Welcome back. Let yourself grow still and let the day quietly slip away. Together, we'll drift slowly through the vast churning storms of Jupiter and Saturn. If nights like this help, subscribe. There's a fresh one every evening. From somewhere above the cloud tops of Jupiter, in the full dark of space, the light arrives at an angle, pale and distant, the sun reduced to a bright point, nearly 5 times farther away than it hangs above the Earth. And yet that light catches something. It catches a surface, or what reads as a surface, from this distance, a continuous rippled expanse of pale cream and white, stretching in every direction, without interruption, curving away at the edges to follow the immense arc of the planet beneath. This is the uppermost skin of Jupiter's atmosphere. It is not solid. It is not liquid. It is a layer of tiny ice crystals, each one formed from ammonia vapor that rose and cooled until it could not stay as gas, and settled into crystalline suspension at temperatures near 130 Kelvin, cold enough that the crystals hold their shape indefinitely, cold enough that no warmth from below can reach this high and disturb them. From here, in the quiet above, Jupiter looks almost calm, almost finished, as if what the eye sees is the whole of what the planet is. It is only the beginning. The ammonia ice cloud deck sits at pressures of roughly half a bar to 1 bar, close to the pressure of Earth's air at sea level, though the resemblance stops there. The temperature is not merely cold, it is the cold of a world that has never known liquid water at its surface, never known the particular warmth that softens things. Light from the distant sun reflects off the crystals in the pale zones, the bright latitudinal bands that circle Jupiter in parallel, and those zones appear luminous, almost glowing, set against the darker belts that weave between them in shades of ochre and rust. From this orbital distance, the whole planet wears its banding like the slow rings of something immeasurably old. The eye settles on it. The mind begins, without quite intending to go still. But every layer seen from above conceals a layer below it. The ammonia ice clouds are the visible face of a structure that descends for hundreds of kilometers, through regions that no light from above has ever reached, through pressures that rise steeply with each passing kilometer downward, through chemical compositions that shift and deepen as the temperature climbs. Jupiter is not a planet with a surface hidden beneath cloud. It is a planet that is atmosphere all the way down, or nearly so, a world of gas and liquid, and at depths too great to visit, metallic states of matter that have no counterpart in ordinary experience. What the eye sees when it looks at Jupiter from space is the uppermost skin of something far deeper, the way the surface of the ocean reads as smooth from altitude, while concealing fathoms of pressured dark. Saturn hangs somewhere farther out in the same darkness, orbiting the same distant sun. Its upper cloud deck is also composed of ammonia ice crystals, also formed in the same cold range of 130 to 150 Kelvin, also stretching around the planet in a continuous layer that catches sunlight and reflects it back into space. But Saturn's version of this same structure looks different. The edges of Saturn's cloud bands are soft, where Jupiter's zones resolve into crisp, high-contrast boundaries. Saturn's banding blurs into gradients, muted tans and warm golds fading into one another rather than meeting in sharp lines. High above Saturn's ammonia cloud deck, a layer of photochemical haze produced by sunlight working on gases in the upper atmosphere scatters and diffuses the light before it reaches the eye. The haze softens everything. It gives Saturn's atmosphere the quality of something seen through old glass, still beautiful, still precise in its underlying structure, but wrapped in a warmth that Jupiter's starker face does not carry. The haze is not decoration, it is chemistry. Sunlight acting on methane and other molecules in the upper atmosphere produces complex organic compounds that settle slowly downward and spread into a diffuse layer above the cloud tops, filtering what would otherwise be sharper, banding into something more gradual, and even on Jupiter, less of this material accumulates in the upper atmosphere, and the banding beneath reads more clearly. On Saturn, the haze is part of the planet's visible identity, the reason it looks the way it does, the soft presence that distinguishes it from its larger neighbor. Even at this first level, the uppermost skin of each world, the two planets are already doing something different with the same physical ingredient. Below the ammonia ice layer on both planets, the atmosphere continues downward into a region that exists in permanent absence of light. No photon from the sun reaches below the ammonia cloud deck in any meaningful quantity. Whatever exists in the layers beneath does so in a cold dark that has persisted since these planets formed, uninterrupted by any day or season in the sense that the outer surface experiences. At depths corresponding to pressures of a few bars, a few times the pressure at Earth's sea level, the temperature has risen enough and the chemical environment has changed enough that a different kind of cloud becomes possible. Here, ammonia and hydrogen sulfide react. They combine under pressure and cold into a compound called ammonium hydrosulfide, and this compound condenses into a cloud layer of its own, distinct from the ammonia ice above it, occupying a band of altitude below the visible surface of both planets. Ammonium hydrosulfide is not a gentle material. In terrestrial terms, hydrogen sulfide carries a strong and unpleasant odor, and its combination with ammonia produces compounds that would be sharply corrosive and deeply unpleasant to any ordinary sense. But here, in the permanent dark below Jupiter's cloud tops, these qualities are simply facts about a chemical environment, properties of a layer existing exactly as it must, given the temperature and pressure and composition of the gas around it. The ammonium hydrosulfide cloud deck is thought to contribute to the brownish and orange colorations visible in Jupiter's darker belt regions, where downwelling atmospheric circulation brings some of this material upward toward the visible cloud tops, or where the chemistry of the region differs enough from the bright zones to produce different compounds and different colors. The precise mixture of molecules responsible for Jupiter's coloration, the specific chromophores, as they are sometimes called, remains one of the genuinely open questions in planetary science, one where the answer exists somewhere in those pressurized dark clouds and has not yet been fully recovered. But the ammonium hydrosulfide layer is part of what produces the visual complexity that makes Jupiter's face so immediately striking from any distance. The color is chemistry. The chemistry is dark. Below that layer, the atmosphere continues downward. The pressure rises. The temperature rises with it, climbing from the deep cold of the upper clouds toward temperatures that would feel more familiar, and then beyond familiar into heat that the body could not endure, at pressures somewhere between 5 and 10 times that of Earth's sea level, deep enough that no light reaches, deep enough that the overlying atmosphere presses down with considerable force. The temperature has climbed high enough for water to exist in liquid form. Here, where the pressure is significant and the heat has accumulated enough to allow it, a water cloud layer forms, not a surface, not a sea in any ordinary sense. A suspended layer of water ice crystals and liquid water droplets existing in the deep atmosphere of a gas giant, unreachable by sunlight, unknown to any instrument that has descended far enough to detect it from the outside. The water cloud layer on Jupiter was not simply predicted and left as a prediction. In December of 1995, a small probe carried by the Galileo spacecraft separated from its parent and descended into Jupiter's atmosphere on a parachute. For roughly 58 minutes, it fell and transmitted. It measured. It sampled the gas around it. It detected winds, temperatures, pressures, and the abundance of various chemical species as it descended through the upper layers of Jupiter's atmosphere. This was the first time any instrument built by human hands had entered the atmosphere of a gas giant and returned data from within it, a singular event in the history of planetary exploration, a moment when a world that had been observed only from the outside received, briefly and under enormous pressure, a visitor from within. The probe's data confirmed the layered structure that models had predicted, including evidence consistent with the deep water cloud region, and measured winds and noble gas abundances that reshaped understanding of how Jupiter's atmosphere was assembled when the solar system was young. The probe itself was eventually crushed by the pressure as it sank too deep to continue transmitting, its last signal extinguished somewhere in the dark layers below. The water cloud layer and the moist, warm region around it is where the energy driving much of Jupiter's visible weather ultimately originates. The latent heat stored in water vapor, the energy released when water vapor condenses into liquid or ice, provides a powerful source of buoyancy that lifts columns of gas upward through the overlying layers, driving the convective motion that eventually reaches the visible cloud tops. But this belongs to a later part of the story. For now, it is enough to understand the layer itself, a hidden interior cloud, suspended in darkness and pressure, too deep for sunlight to find, composed of the same simple molecule that covers most of Earth's surface, existing in a place that nothing built on Earth could visit and survive. The water cloud on Jupiter is real. It is there. It has been, in the most direct sense possible, detected. The atmosphere of Jupiter does not end with these three main cloud layers. It continues downward through regions where the pressure rises steeply, driven by the planet's surface gravity, approximately 24.8 meters per second squared, nearly 2.5 times the gravitational pull at Earth's surface. This is the force that compresses the gas above into the pressures that produce the clouds. It is the force that makes the atmosphere dense enough in the upper layers to be opaque, and it is the force that drives pressure upward quickly, with depth, so that descending even a few hundred kilometers below the visible cloud tops brings the surrounding atmosphere to pressures of tens of bars, far beyond what the Galileo probe survived, far beyond what any instrument has yet descended to reach. Under Jupiter's gravity, the atmosphere deepens rapidly. The skin of cloud and gas that the eye sees from space is a thin veneer above a column of compressed atmosphere that extends downward for thousands of kilometers before the gas transitions to something other than gas. Saturn's gravity is weaker. At roughly 10.5 meters per second squared, it is somewhat more than Earth's surface gravity, but considerably less than Jupiter's. The consequence for the atmosphere is that the same vertical column of gas produces lower pressures at any given depth. The same cloud layers exist, the ammonia ice at the top, the ammonium hydrosulfide below, the water cloud deeper still, but they are spread farther apart in altitude, separated by greater vertical distances, arranged in a structure that is more gradual and more extended than Jupiter's more compressed version. Saturn's atmospheric column is, in a sense, more spacious. The layers are spaced wider. The pressure gradient is gentler. Where Jupiter's atmosphere compresses rapidly with depth, Saturn's opens more slowly, stretching the same chemical architecture across a taller vertical extent. This difference in gravity is one of the reasons the two planets, though made of broadly similar materials and formed in similar circumstances, feel different when studied closely. Saturn is larger in diameter than Jupiter's core alone might suggest, because its lower gravity allows its gas to occupy a greater volume. The planet is less dense than water, so much less dense that it would float, in theory, on a large enough ocean, a consequence of having a lower interior pressure than Jupiter, despite being nearly as large. Every layer in Saturn's atmosphere sits at a slightly different altitude than the equivalent layer on Jupiter, and the chemistry unfolds across a longer vertical distance, the whole structure stretched and softened by the weaker pull from below. The boundary between the convectively active lower atmosphere and the more stable upper atmosphere, the tropopause, sits at pressures of roughly 100 to 200 millibars on Jupiter at altitudes just above the visible ammonia cloud tops. At this level, temperatures reach a minimum near 110 Kelvin. Above the tropopause, the temperature stops falling with altitude and begins to rise again because different physical processes dominate in the stable stratosphere above. The stratosphere is not where the great storms and cloud systems live. It is a quieter domain where chemistry driven by solar ultraviolet light produces complex molecules, where temperature is shaped more by radiation than by the convective churning going on beneath. Below the tropopause, the atmosphere is alive with vertical motion. Above it, things settle into a different kind of stillness. On Saturn, the stratosphere carries a quality that Jupiter's does not express in quite the same way. Saturn's axial tilt is approximately 26.7 degrees, close to Earth's own tilt of 23.5 degrees, and far greater than Jupiter's nearly upright 3 degrees. This tilt means that Saturn has seasons, not seasons in the sense of warmth and cold, cycling quickly year to year, because Saturn's year is nearly 30 Earth years long, and so each season spans the better part of a decade in Earth time. As Saturn moves through its long orbit, first one hemisphere and then the other receives more direct sunlight. The stratosphere responds. The stratospheric temperature in the sunlit hemisphere rises, slowly, over years, as the geometry of the planet's orbit gradually delivers more solar energy to that pole and that hemisphere. The shadowed hemisphere cools with equal gradualness. The change is slow enough that it cannot be felt in the span of a human observation season. It requires years of watching, years of measuring, to detect the temperature difference accumulating. The first detailed thermal mapping of Saturn's stratosphere came from the Cassini spacecraft, which arrived at Saturn in 2004 and remained in orbit until 2017, 13 years of continuous observation as Saturn moved through nearly half of one complete orbit. During that time, Saturn's northern hemisphere passed from winter through equinox and toward summer solstice in 2017, a slow reversal of illumination that Cassini's instruments tracked in temperature, in chemistry, and in the color and composition of the hexagonal polar cloud system. The stratosphere warmed where it had been cold. The cold shifted south. The whole planet breathed, in a way, through the long turning of its orbit, its upper atmosphere responding to the light with the measured patience of something very old and very large. Jupiter, with its nearly upright axis, does not have this. Its seasons are negligible. The difference in solar illumination between its two hemispheres at any point in its orbit is too small to produce meaningful seasonal temperature swings. Jupiter's stratosphere is more uniform, its temperature structure more constant from north to south, its chemistry not cycling with the particular rhythm that Saturn's slow seasonal turn produces. Where Saturn's upper atmosphere shifts through visible chromatic changes, accumulating photochemical haze in summer hemispheres and thinning it in winter. Jupiter's stratosphere operates in something closer to a steady state, its year too short and its tilt too small for the large-scale seasonal cycling that defines Saturn's long atmospheric rhythm. The pale cream expanse of Jupiter's ammonia ice layer rests at the top of all of this. The soft, haze-blurred banding of Saturn's upper cloud deck rests above its own layered depth. In both cases, what is visible from outside the atmosphere is only the topmost fraction of a structure extending hundreds of kilometers downward through chemical complexity, rising pressure, and permanent dark. The clouds that are seen are real, precisely measured, and understood in considerable detail. The layers beneath them are known partly through inference from physical models, partly through the evidence of remote sensing instruments that can probe some depth below the visible surface, and partly through the direct measurement made by one descending probe on one cold December day a generation ago. The picture is not complete. It is detailed enough to be inhabited, to be understood in its broad architecture, but the precise contents of the layers below the water cloud and the exact nature of the chemical color agents that produce the Jovian palette remain questions that the science holds open. And open questions in this context are not absences. They are spaces where the picture is accurate to its limits and honest beyond them. The three main cloud layers on both planets, ammonia ice, ammonium hydrosulfide, and water cloud, are not speculation. They are the outcome of physical chemistry applied to the known temperature and pressure profiles of these atmospheres, confirmed at multiple levels by spacecraft observation and atmospheric probing. The layered structure is real, the depths are real, the pressures are real. What changes between one look and the next, between one measurement and the one made decades later, is not the structure, but the resolution. Each new instrument, each new mission, each new decade of theoretical development allows the picture to be drawn with finer lines. The cloud tops that Voyager photographed in 1979 were the same cloud tops that Cassini photographed 30 years later and that Juno has imaged since. They have not changed in their fundamental nature. What has changed is the depth to which human understanding has reached into them, the precision with which the chemical layers below have been mapped, the thickness of knowledge laid down around them by years of patient observation. The ammonia ice crystals in Jupiter's uppermost cloud layer are approximately 1 to 10 micrometers in size, smaller than the width of a human hair, small enough that they remain suspended almost indefinitely in the gas around them, drifting and tumbling slowly in the slow currents of the upper atmosphere without falling through to lower levels. Their small size is part of what makes the cloud deck opaque. There are so many of them spread across such a large area that sunlight cannot penetrate through them to reach what lies below. The cloud deck acts as a ceiling for the planet's interior. Everything beneath it exists in a darkness that the outer solar system's sunlight has never touched. On Saturn, the same tiny crystals perform the same function, but with the additional softening layer of photochemical haze above them. The haze particles are even smaller, the scale of individual molecules clustered into tiny aggregates, and they scatter light differently than the larger ice crystals below, producing the diffuse, warm-toned appearance that distinguishes Saturn's upper atmosphere from Jupiter's crisper, higher contrast face. The haze does not block light as effectively as the cloud deck below it. It filters it. It blurs the sharp edges that would otherwise be visible. It gives Saturn the quality of something seen at a slight remove, like a landscape in morning mist that is still fully there, but rendered in softer lines. Where Jupiter's equatorial zone appears as a bright, almost luminous band of reflected ammonia cloud. The prograde equatorial jet and the rising atmospheric columns associated with it, causing the upper cloud material to be consistently thick and reflective. Saturn's equatorial region is hazier, its brightness toned down by the overlying photochemical layer. Both planets' cloud tops reflect a large fraction of incoming sunlight, giving them high albedos, but the character of that reflection differs between them in ways that are immediately visible even in a small telescope. Jupiter glares slightly, Saturn glows. The geometry of these two planets in their respective orbits places them at very different distances from the Sun, and the sunlight arriving at their cloud tops is correspondingly different in intensity. At Jupiter's average orbital distance of roughly 5.2 times Earth's orbital distance, the sunlight arriving is approximately 27 times less intense than at Earth's surface. At Saturn's average of about 9.5 times Earth's orbital distance, it is more than 90 times less intense. The upper cloud layers of both planets exist in a dim solar environment compared to what Earth's surface receives, and yet that faint sunlight is enough to drive photochemistry in the upper atmosphere, to warm the stratospheric layers to a temperature that maintains a stable inversion above the tropopause, and on Saturn, to produce the slow seasonal warming that shifts temperatures across the long arc of the planetary year. The tropopause itself, that boundary between the convective lower atmosphere and the stable stratosphere above, is not a sharp surface. It is a transition zone, a few tens of kilometers in vertical extent, where the temperature gradient changes sign from cooling with altitude to warming with altitude, where the character of atmospheric motion shifts from turbulent and convective to more laminar and stable, where the chemistry of the upper atmosphere gives way to the chemistry of the lower. On both planets, this region sits just above the visible cloud tops, above the ammonia ice layer, at pressures of roughly 100 to 200 millibars on Jupiter, and at similar or slightly different pressure levels on Saturn. It is the ceiling of the weather that gives these planets their visible faces. Above the tropopause, in the stratospheres of both planets, the atmosphere becomes progressively more transparent. The haze particles and ice crystals that populate the lower cloud layers are largely absent here, and the gas above the tropopause allows sunlight to pass through to the cloud tops below, rather than scattering it back to space. The stratosphere receives some ultraviolet energy from the sun, which it uses to drive photochemistry, but it does not participate in the convective dynamics that shape the visible cloud patterns. It is a quieter realm. Temperature changes here are driven by radiative processes, by the absorption and emission of infrared light, and by the slow seasonal cycles of solar illumination, rather than by the latent heat release and convective overturning that fill the troposphere below with its currents and cloud layers. On Saturn, the stratospheric seasonal cycle is measurable. Cassini's infrared instruments mapped temperature changes in Saturn's stratosphere across the full arc of its observing mission, detecting the gradual warming of the northern hemisphere's upper atmosphere as that hemisphere moved from winter through equinox towards summer. The temperature changes involved are small in absolute terms, a few Kelvin over years, but they are real, and they track with the geometry of Saturn's orbit in ways that confirm the planet's seasonal responsiveness. A world that takes nearly 30 years to complete one circuit of the Sun experiences each season as a multi-year epoch. The stratospheric temperatures shift slowly through those epochs, warming where sunlight increases, cooling where it diminishes, the whole upper atmosphere breathing in long, slow rhythms tied to the planet's orbital position. This slow breathing continues after any observation of it ends. Saturn does not pause in its orbit when instruments stop watching. The stratospheric temperature continues to shift, degree by slow degree, as the planet moves through space. The northern hemisphere, which had reached summer solstice in 2017, will have passed beyond it, and will slowly cool again over the years that follow. The southern hemisphere, which was deep in winter when Cassini first arrived at Saturn in 2004, will eventually warm again as the planet's orbit carries it toward its own summer in another decade and a half. The cycle turns. It has been turning since Saturn formed, which was close to 4.5 billion years ago, long before there were eyes or instruments to measure it. The ammonia ice crystals at the top of Jupiter's atmosphere do not know about this. They drift and tumble in the cold at temperatures near 130 Kelvin, reflecting the faint light of the distant sun back into space with quiet efficiency. Below them, in permanent dark, the ammonium hydrosulfide cloud waits at its deeper pressure level, existing exactly as it must. Below that, deeper still, where the pressure is 10 times what any surface on Earth provides, the water cloud layer floats in warmth and dark. And below that, the atmosphere continues downward, past the limits of any probe that has yet descended, into pressures and temperatures that physical models describe in detail, but no instrument has yet confirmed by direct measurement. The visible face of Jupiter, that pale cream expanse of ammonia ice cloud, those alternating bands of light and dark that the eye sees first and finds arresting, is the topmost leaf of something that extends for hundreds of kilometers downward and for tens of thousands of kilometers in every horizontal direction. The visible face of Saturn, softer, warmer in tone, its edges blurred by haze, covers the same kind of depth, the same kind of layered chemical architecture, stretched slightly by Saturn's weaker gravity into something more gradual and widely spaced. Both planets wear their atmospheres as the outermost expression of a deep internal structure, and the clouds the eye catches from space are only where that structure happens to become visible. The outermost ammonia ice layer on Jupiter drifts in cold sunlight at 5 times Earth's distance from the sun, reflecting light, radiating heat slowly into the dark around it, unchanged in its fundamental nature from the cloud tops that the earliest spacecraft photographed. The layers below are unchanged too. The ammonium hydrosulfide layer in its permanent dark, the water cloud in its deep warm pressure, and Saturn, farther out, moves through the slow progression of its year, the seasons turning over decades, the stratospheric temperature rising or falling in the hemisphere that the sun is touching. The haze above Saturn's cloud tops thickens slightly in summer and thins slightly in winter, the chemistry responding to the light with the patience of processes that have been operating for nearly as long as the solar system has existed. In the stratosphere above Saturn's northern clouds, where the summer light has been building for years, the temperature is a few degrees warmer than it was a decade ago. The planet moves in its orbit. The angle of sunlight changes by increments too small to notice in any individual year, and over the course of years that accumulate into decades, the stratosphere warms where it is lit and cools where it is not. The slow seasonal rhythm of a tilted world carrying its upper atmosphere through the long, patient turning of its year. The change is real. It continues. It requires no witness to persist, and will go on turning long after any particular observation of it has ended. Codpel, cream band, at Jupiter's equator catches sunlight from 500 million miles away, and along its southern edge, something is happening that no single eye could track. A ribbon of gas, invisible in itself, is moving It has been moving since before any instrument existed to measure it. It runs parallel to the equator with a precision that a surveyor would recognize, following no boundary drawn in matter, only a boundary drawn in pressure and rotation and the deep physics of a planet that weighs more than all the other planets in the solar system combined. The ribbon circles the entire world without stopping, without a gap, without a seam. It moves at roughly 150 meters per second. That is fast enough to carry a parcel of air from one side of North America to the other in less than half an hour, and it does this not for a season, not for a year, but continuously, decade after decade, a river flowing in a loop that has no beginning and no end. This is Jupiter's equatorial jet stream, and it is one of several dozen such rivers currently encircling the planet. Each one runs east or west, each one remains locked at its latitude, and each one, taken together with the ones running beside it in the opposite direction, produces the pattern that any telescope aimed at Jupiter will resolve, alternating bands of pale and dark, cream and ochre, stretching from equator to pole in near-perfect parallel lines, as regular as the rings on a cut tree, as old as anything the inner solar system has ever watched from a distance. The pale bands are called zones. The dark bands are called belts. Those two words carry more than color. They carry the entire vertical architecture of a planet's weather compressed into a single visible surface. Where a zone appears bright, gas is rising from below, lifting cold ammonia crystals into the upper atmosphere where sunlight reflects off them in pale whites and creams. Where a belt appears dark, gas is descending, drawing warmer material down from above and pulling the bright cloud layer thin, letting the deeper, chemically richer layers show through in shades of brown and orange and rust. The line between a bright zone and a dark belt is not a gradual transition, it is sharp. Seen from close orbit, it can look like a color boundary drawn by a steady hand, a clean edge running for thousands of kilometers along a curve of latitude, separating rising gas from sinking gas with no middle ground between them. The sharpness of that boundary is itself a clue. On Earth, the division between rising and sinking air tends to dissolve and reform, to wander and meander, to break down into spiraling weather systems, and then reconstruct itself days later somewhere else. The boundaries on Jupiter hold because the jet streams that form them are not shallow. A jet stream confined to the thin weather layer at the top of an atmosphere can be pushed sideways, disrupted, tilted by mountains or ocean temperature gradients, all the irregular surfaces that interrupt a planet's lower atmosphere. Jupiter has none of those surfaces. Its atmosphere deepens for thousands of kilometers without a solid boundary to deflect it, and a jet stream with nothing to push against from below is a jet stream that stays exactly where the physics of a rotating planet places it. Saturn carries its own system of jet streams, and they run faster. The equatorial jet on Saturn reaches speeds of 400 to 500 meters per second, almost half a kilometer every second, sustained and unbroken around a planet roughly 9 times the diameter of Earth. A continuous loop of gas at that speed, on that scale, is something the inner solar system has no equivalent for. The wind speeds of Earth's jet streams, powerful enough to redirect commercial flight paths and reshape weather across continents, are a fraction of what Saturn's equatorial river runs at. And yet Saturn's banding appears softer, its color contrasts less vivid than Jupiter's. The darker belts and brighter zones are still there, still running parallel to the equator, but they arrive blurred and muted, as if the same image had been slightly defocused. Its edges spread into gradients rather than lines. High-altitude haze sits over Saturn's cloud tops in a way that has no precise counterpart on Jupiter, spreading and softening the contrast between adjacent bands into something more diffuse and dreamlike, the colors fading into each other across kilometers of suspended aerosol, rather than ending cleanly at a wind boundary. Both planets, then, show the same basic organizing principle: alternating rivers of wind, running east and west in opposing pairs, creating the visible pattern of bands on the surface. Jupiter shows it sharply, Saturn shows it in a softer register. But on both planets the principle holds, and on both planets the question that took longest to answer was the same: how deep does it go? A jet stream in Earth's atmosphere exists in the lower 10 or 15 miles of the air. Everything above that level is essentially still by comparison. The jet is a weather layer phenomenon. It arises from temperature gradients at the surface, from the contrast between warm tropical air and cold polar air, and when those gradients shift seasonally, the jets shift with them. The expectation, when scientists first began modeling Jupiter's atmosphere in detail, was that something similar would apply, that Jupiter's jets were surface features, skin-deep expressions of weather at the top of a very deep gas planet, unconnected to anything below the visible cloud layer. The planet's interior was imagined as something like a deep, calm ocean, too uniform and too pressurized to sustain the organized flow of the bands visible at the surface. The bands on this picture would thin out and vanish within a few hundred kilometers of the cloud tops. Below that, the planet would be essentially blank, rotating more or less as a solid body, undifferentiated, featureless. The measurements that tested this picture arrived slowly and from several directions. The most direct came from a spacecraft whose microwave radiometer instrument could sense not just the visible surface of Jupiter, but the gas many hundreds of kilometers below it. By recording the thermal emission rising from progressively deeper layers, and the instrument built up a picture of what the atmosphere looked like, far beneath the ammonia cloud deck. And what it found was organized structure continuing downward through depths that the shallow jet model had predicted would be blank and uniform. The jet streams were not stopping. They were continuing. They were present, coherent, and organized at depths of at least 3,000 kilometers below the visible cloud level, extending through layers that no light from the sun had ever reached, through pressures tens of times those at the surface of Earth, through gas so dense and so dark that the word atmosphere begins to feel inadequate for what it describes. 3,000 kilometers is a distance that takes some holding. It is roughly the distance from the Gulf of Mexico to the Arctic Circle. If a column of gas rose vertically from the deepest resolved layer of Jupiter's jets to the pale ammonia cloud tops, it would need to travel farther than the full width of the continental United States. And through all of that vertical distance, through every layer of that dark pressurized column, the organized east-west flow persists, coherent and directional, turning steadily with the same sense of rotation it carries at the top. The planet's gravity makes this even harder to absorb at first. Jupiter's gravity at its cloud tops is already more than twice Earth's surface gravity. Beneath the clouds, as pressure rises steeply with depth, the density of the atmosphere climbs rapidly too. Maintaining an organized flow of gas in a medium that dense, across that vertical extent, against the tendency of any fluid to homogenize and randomize over time, requires either continuous energy input from below, or conditions of rotation and density, stratification that suppress mixing across latitude lines. Jupiter's fast rotation, it completes a full turn in just under 10 hours, provides some of that suppression. A rapidly rotating planet has a strong tendency to organize fluid motion into columns aligned with the rotation axis, a tendency named after the physicist who first described it in the context of rotating fluids. That tendency, combined with the planet's deep atmospheric structure, appears to be part of what keeps the jet streams coherent over such enormous vertical distances, though the complete picture remains an area of active investigation. The same mission that detected the jets at depth used the planet's own gravity field to push that picture deeper still. As a spacecraft orbits a planet, the gravity field of the planet tugs at it in ways that reflect the distribution of mass inside. A planet whose mass is distributed perfectly uniformly pulls on an orbiting spacecraft in a perfectly simple, symmetric way. A planet with internal structure, dense material concentrated unevenly, or internal flows that redistribute mass from one latitude to another, leaves subtle asymmetries in the gravity field that can be measured by tracking the spacecraft's path with extraordinary precision. Jupiter's gravity field, measured across many orbital passes, showed asymmetries that could be attributed to its zonal wind flows. The flows themselves were distorting the distribution of mass within the planet, and that distortion was leaving a faint gravitational imprint on spacecraft thousands of kilometers overhead. The depth at which those gravitational signatures ceased matched calculations suggesting that Jupiter's jet streams persist at depths where the pressures approach something in the range of 100,000 bars, 100,000 times the pressure at Earth's sea level. At those depths, hydrogen behaves not as a gas or even as a compressed fluid, but as something that conducts electricity, a state called metallic hydrogen, in which the electrons no longer belong to individual atoms, but flow freely through the material the way they do in a metal. Metallic hydrogen rotating in Jupiter's interior is thought to generate the planet's intense magnetic field, and it rotates very nearly as a solid body, meaning that all parts of the metallic interior at any given latitude turn at the same rate. Without the relative motion between layers that defines a flowing wind, the transition from the zonal jet streams above to the solid body rotation of the metallic interior below is not a sharp boundary, but a gradual one, a deepening of coupling between adjacent layers as the conductivity of the hydrogen increases and the magnetic field begins to break any differential flow. The jets fade into the interior not by stopping abruptly, but by gradually merging with it, the organized atmospheric circulation dissolving over tens of thousands of kilometers of increasing depth into something that rotates as one. On Saturn, the jets reach deep too. The lower gravity and different internal structure mean that the exact depths are still being worked out, and the picture is less complete than for Jupiter, but the principle appears to hold. The winds visible at Saturn's cloud tops are expressions of organized flow extending well below the visible surface, shaped by the same planetary scale physics that governs its larger neighbor. It is worth pausing here with the slow, specific fact of what Saturn's equatorial wind means in terms of distance. Saturn's equator is a circle roughly 360,000 kilometers around. A parcel of air in Saturn's equatorial jet stream, moving at 450 meters per second, a midpoint in the range of measured speeds, would complete one full circuit of that equator in a little under 9 Earth days. Not in a year, not in a month, in 9 days. The entire planet encircled at that speed continuously, and that wind does not push against coastlines, does not break over mountain ranges, does not slow over cold ocean surfaces. There is nothing to slow it. It runs in its loop with nothing opposing it but its own internal dynamics and the subtle drag of the magnetic field far below, and it has been running since Saturn formed billions of years ago, settling into its present configuration over stretches of time that dwarf the entire span of complex life on Earth. The boundary between a zone and a belt on Jupiter, seen from close orbit, is one of the more precise natural lines anywhere in the solar system. The pale zone on one side and the darker belt on the other are separated by a narrow transition that in resolved imagery looks almost like a painted edge. That edge marks something that cannot itself be seen, the line between two opposing jet streams, one moving eastward, one moving westward, their shear producing a current along the boundary in the same way that two rivers moving in different directions along their shared bank generate a region of turbulence between them. On Jupiter, those turbulent boundary regions sometimes resolve into small eddies and cloud filaments, braided structures visible in the highest resolution images as intricate weavings of light and dark material drawn into the flow of the opposing jets. The eddies are small by Jovian standards, a few hundred kilometers across, little larger than a tropical storm on Earth. They form, drift, and dissolve over days to weeks, constantly replaced by new ones forming at the same boundary. Across millions of square kilometers of Jovian atmosphere, along every zone belt boundary, at every latitude, this process runs continuously, these small circulations spinning up and fading in the margins of winds that have been flowing since before the solar system had its present arrangement. The deeper identity of the darker belt coloration remains an open question. The ammonium hydrosulfide cloud layer, below the ammonia cloud deck, contributes some of the brownish tones visible in the belts, where the thinning of the bright upper cloud layer allows the color of the material below to show through. But the precise molecular identity of the compounds responsible for the deeper oranges and reds, the warmest tones of the Jovian belts, is not fully settled. Sulfur compounds and phosphine brought up from depth by the downwelling circulation are among the candidate chromophores, that is, the molecules that absorb certain wavelengths of light and reflect others, but the chemical pathways that would produce specific observed colors under Jovian atmospheric conditions involve complex photochemistry that has not been fully reproduced in laboratory conditions. The color of Jupiter's belts is not a mystery in the sense of being incomprehensible. It is a question with several good candidate answers and no definitive resolution yet. The planet has been watched and measured for centuries without yielding the final answer to that particular question, and it has not been for lack of attention. Saturn's visible banding tells a somewhat different chemical story. The same basic layers are present below the cloud tops, ammonium hydrosulfide, and below that the water cloud layer, but Saturn's atmosphere shows less variation in belt coloration than Jupiter's. The overall palette of Saturn's visible atmosphere runs from pale cream to warm gold to faint tan, without the rich rust and brown tones that mark Jupiter's darker belts. Part of this difference may reflect atmospheric circulation. Saturn's deep circulation may be less vigorous at bringing strongly colored material upward from the lower cloud layers into the visible atmosphere. Part of it may reflect the higher altitude haze layer that softens everything above it, and part of it may reflect real differences in atmospheric chemistry between the two planets, differences in the abundance of specific compounds, in the rates of photochemical reactions driven by the differing intensities of sunlight at Saturn's greater distance from the Sun, in the temperature profiles of the two atmospheres at the levels where chromophore chemistry is most active. The softer palette of Saturn is not the absence of structure, but a structure differently expressed, the same organizing forces, the same layered architecture, the same system of opposing jets, rendered in quieter colors at greater distance from the Sun. Looking at the zone belt boundaries on either planet is a way of reading wind without a wind gauge. The color transition is not itself the wind, it is the visible consequence of the wind, the surface expression of an invisible force that runs thousands of kilometers downward into darkness. This is a habit the outer planets reward, reading the surface for what it cannot show directly, inferring the deep from the shallow, tracing enormous invisible structures by the small marks they leave on the top of the atmosphere. The pale cream of the zones is not just a color, it is the top of a rising column of gas. The darker orange of the belts is not just a tint, it is the surface of a descending column, pulling the upper cloud deck thin, pulling warmer and chemically different material upward from below, through the sheer mechanics of a sustained downwelling that has been in place since before human telescopes existed to document it. The opposing jets that define the zone belt pattern do not sit still in a vacuum. They interact with each other across their shared boundaries. They interact with the storm systems that form within and between them. The large oval vortices that persist for years or decades inside the stable channels between adjacent jets, held in place by the same flow that would otherwise shear them apart. They interact with the planet's deep interior through the coupling that the gravity field measurements revealed, a connection between surface wind and interior structure that runs all the way down to the magnetic field and back, and they are themselves in a slow, extremely gradual state of change over very long timescales, shifting slightly in speed and position, with the south equatorial belt on Jupiter known to occasionally fade nearly to invisibility before reviving again, and Saturn's jet structure evolving subtly over the decades that spacecraft have been watching it. That slow evolution is part of what makes these systems so different from the weather systems of the inner planets. On Earth, a major weather pattern lasts days to weeks. On Jupiter, a jet stream has been in its current location and running in its current direction for at least as long as careful observations have existed, and probably for far longer. The time scale of change for a Jovian jet stream is not seasons or years, but centuries or longer, a persistence that belongs not to weather, but to something more like geology. The kind of change that happens so slowly, it is effectively invisible within a human life, detectable only by comparing measurements taken centuries apart. The equatorial jet on Saturn is the most extreme example of this persistence. At 400 to 500 meters per second, it is among the strongest continuous wind flows anywhere in the solar system. It has been running at those speeds, around that equator, for longer than any estimate of planetary atmospheric timescales can easily quantify. The Voyager spacecraft measured it in 1980 and 1981. Later observations refined the measurement and found the speed consistent, the jet present, the structure intact. Decades of observation from orbit added more data, and through all of it, the equatorial jet stream ran as it had always been running, eastward, unbroken, at nearly half a kilometer per second, encircling a planet 9 times the width of Earth in a continuous loop that carries no cargo, serves no purpose in the human sense of purpose, and has no destination other than the place it departed. There is something settling in that image. A wind that large, that old, that steady. It is not a dramatic thing in the way that a storm is dramatic. It is quiet in its scale. The belts and zones of Jupiter are not turbulent in the places the jets flow most cleanly. They are organized, parallel, precise in their latitudes, as regular as the grain of carefully split wood. The opposing rivers of gas run side by side in their opposing directions, decade after decade, and between them the atmosphere finds its color and its chemistry and its cloud patterns, everything arranged along the lines that planetary rotation drew into the gas at the very beginning, and that the deep structure of the planet has maintained ever since. That regularity, that deep unhurried persistence, is what the visible banding of both planets is saying when seen from orbit. It is not chaos, it is not the turbulent scramble of weather on a small, warm, geologically complex world. It is something more like the interior of a machine that has been running undisturbed for billions of years, not mechanical in the sense of being cold or empty, but ordered in the way that a very large, very slow, very deep physical system finds its own natural organization, and then holds it year after year and century after century, while the small bright planets of the inner solar system spin through their fast seasons and quick geological cycles far away. The jet streams visible at Jupiter's cloud tops, running their opposing courses around the planet at 150 meters per second, carry that enormous downward depth in their motion, 3,000 kilometers of organized, coherent flow below every visible stripe of cloud, and below that, the faint coupling to a metallic interior rotating as a single body, the whole structure connected from the surface down to the magnetic field, from the thin ammonia cloud deck at the top to the strange and pressurized dark of a planetary deep that no instrument has directly visited and that light from the sun has never reached. The banding is a surface. Below it, the planet stretches downward for distances that put the word atmosphere under strain into regions where pressure and density and the nature of matter itself change so completely that the gas at the top and the metallic fluid at the bottom are almost different substances, joined by a continuous gradient of increasing extremity that descends for tens of thousands of kilometers without interruption. And somewhere in the middle of all of that, at depths beyond the 3,000 kilometers where the jets have been directly resolved, at pressures that no human instrument has yet reached and measured, the wind continues. It is still flowing east. It is still flowing west, organized, ancient, and entirely indifferent to the long patience of the scientists measuring it from above. The belts and zones of two worlds hold their lines across distances that dwarf anything the inner solar system offers, roots reaching down to where the planet itself begins, flowing through the dark with the slow, enormous certainty of something that has been in motion long enough that stillness is the only thing it has never been. Deep in the atmosphere of Jupiter, far below the pale cream cloud tops that catch the distant sun, a pocket of warm gas begins to rise. It rises because it is lighter than what surrounds it. It carries water vapor and the heat of a planet that generates as much energy from its own interior as it receives from the sun 80 million miles away. The pocket climbs through darkness, through increasing cold, through layers of pressure that would flatten any machine built on Earth. It rises slowly at first, then faster as the temperature difference between it and the surrounding air grows, the way a bubble in warm water rises more urgently as it nears the surface. This single quiet event, a buoyant pocket of gas beginning to climb, is how nearly every storm on Jupiter and Saturn begins. The process has a name that comes from the way moisture moves. Moist convection. It is the same basic mechanism that generates a thunderstorm on a warm afternoon over the fields of a continent, except that on Jupiter, the water cloud layer, where this lifting originates, sits at depths where the pressure is 5 to 10 times what presses down on the surface of the sea. The column of rising gas has to travel through hundreds of kilometers of atmosphere before it reaches the visible cloud tops. Through the water cloud layer, through the ammonium hydrosulfide deck above it, through the ammonia ice layer at the top. Each threshold marks a change in chemistry, in temperature, in the character of what the gas carries. By the time the rising column punches through the highest cloud deck and blooms outward into the cold near vacuum of the upper atmosphere, hours or days may have passed. What arrives at the visible surface looks like a bright white convective plume, a billowing head of fresh ammonia ice crystals spreading out in all directions from the point of eruption, brighter than the surrounding cloud bands and cold in a different way than what lies beside it. That plume is not just a cloud. It is the visible tip of a deep disturbance, the uppermost expression of a column of energy that has been building from the bottom of the troposphere, and the beginning of something that may persist for years. The storms that form on Jupiter and Saturn are not like storms on Earth in their longevity. On Earth, even the largest hurricane dissipates in weeks, shredded by wind shear, starved of the warm water that sustained it, dispersed into the general circulation of the atmosphere. On Jupiter, the conditions that sustain a storm can persist not for weeks, but for decades, for centuries. The planet's atmosphere has no solid surface to drag on the base of a circulation system and slow it down. The jet streams that encircle the planet at fixed latitudes act instead as walls, confinement structures that keep the rotating mass of a storm from spreading out and collapsing. A vortex that forms within such a confinement can spin for a very long time, not because it is exceptional, but because the conditions that allow it to persist are the ordinary conditions of that latitude. Oval BA is one such vortex. It is a storm in Jupiter's southern hemisphere, and it did not always have that name. For roughly 6 decades, 3 separate white oval storms drifted in the south temperate belt, their circulations running in parallel, each distinct, each bounded by the jet streams on either side of the belt. They were called FA, BC, and DE, the names assigned from their cloud feature letters by observers tracking them across successive images. Each was large by any earthly measure. Each had its own internal circulation, its own boundary, its own slowly evolving shape, and for 60 years they orbited the planet alongside one another at slightly different speeds, drifting in the current of the surrounding atmosphere without merging. Then, in 1998, 2 of them began to touch. The mathematics of vortex dynamics governs what happens when 2 rotating systems of the same sense approach each other inside a confined jet stream environment. When 2 anticyclones both rotating the same direction drift close enough together, their outer circulation bands interact. Das Ruf something begin, but the fluid between them begins to move in a manner that draws them closer. They do not simply collide. They circle around one another, approaching gradually, the boundary between them thinning and thinning until the 2 separate circulations begin to fold into one. The process takes time. It takes months of slow orbital dance before the 2 storms are truly one. The merged result in 1998 was a single oval, larger than either predecessor, inheriting the combined angular momentum of both. Then, in 2000, that merged vortex encountered the third, DE, and the same slow process unfolded again. The 3 had become one. The new unified storm was named Oval BA. For years after its formation, Oval BA appeared white, like its predecessor ovals, a pale circulating cloud mass drifting quietly in the south temperate belt. Then, its color began to change. Slowly, over the course of years, its center deepened from white toward cream, and from cream toward a reddish brown that by around 2006 had taken on a hue similar in character to the great red spot that dominates the same hemisphere, but at a different latitude. Scientists considered various explanations for this reddening. The best current picture involves the upward transport of chemical compounds from deeper in the atmosphere, materials tinted by sulfur or by complex molecules that form under the specific pressure and temperature conditions of the lower cloud layers, brought up as the storm's central circulation draws gas from below. The reddish coloration of the Great Red Spot itself may arise from similar chemistry, which is why the color change in oval BA attracted such attention. It suggested that the smaller storm had deepened its circulation enough to begin drawing from the same dark reservoir that has kept the Great Red Spot its distinctive color for as long as anyone has watched. Oval BA still drifts in the South Temperate Belt. It is smaller than the Great Red Spot, but it is old now in its own right, and it turns through the belt's confinement as steadily as anything in that atmosphere does. The Great Red Spot sits at a latitude of about 23 degrees south. It is an anticyclone, a high-pressure system rotating counterclockwise in the southern hemisphere, opposite to the direction a northern hemisphere cyclone would spin on Earth. Its outer edges are braided with cloud filaments pulled in and partly wrapped around the storm's perimeter by the differential motion between the storm's circulation and the ambient jet stream flow. The interior is a deep brick red at its darkest, surrounded by a lighter orange ring, and from directly above it has the shape of an oval with its long axis running east to west, parallel to the equator. In the 19th century, when records of its diameter were first made with enough precision to compare, it spanned roughly 40,000 kilometers from end to end, large enough to contain 3 Earths placed side by side across its widest dimension. In the late 20th century, it had shrunk to around 25,000 kilometers. Today, it is closer to 14 to 16,000 kilometers in its east-west extent. The shrinkage has been gradual and has continued without interruption across decades of observation. No single cause has been definitively established. The storm maintains its internal circulation, its distinctive color, its position relative to the surrounding jet streams. But it is measurably smaller than it was, and measurably smaller than it was a decade ago, and smaller again than a decade before that. Whether this represents a long, slow decline that will eventually bring the storm to an end, or whether the shrinkage will stabilize at some smaller equilibrium size, remains an open question. Some models suggest the storm could become more circular as it contracts, evolving toward a more compact and potentially stable vortex structure. Others suggest the opposite, that below some threshold size, the confining dynamics of the surrounding jet streams become insufficient to maintain the circulation, and the storm would then weaken and dissipate. The honest position is that no one knows which path the Great Red Spot is on. What is known is that it has been turning for a very long time. The first written records that may describe the Great Red Spot date to the 1600s. There is a reference in the historical literature to a prominent feature observed by Giovanni Cassini in the latter decades of the 17th century, a feature sometimes interpreted as the same storm, though the evidence is not conclusive. The continuous and unambiguous record begins in the 1830s, which is itself an extraordinary fact, an atmospheric feature that has persisted in one form or another for nearly 2 centuries, through everything that time implies, the slow drift of human generations, the rise and fall of entire technologies of watching. The telescope that tracked it in the 1830s was made of glass and brass. The spacecraft that images it today carries instruments that encode light as numbers and transmit them across the distance between worlds. Through all of that, the storm turned. The counterclockwise rotation of the Great Red Spot completes one full cycle, roughly every 6 days, a period measured by tracking the drift of cloud features within the storm relative to the ambient belts around it. The outer edge of the storm moves faster than the interior. The very center, the deepest part of the circulation, rotates most slowly of all. This differential rotation, fast at the rim, slow at the core, is another characteristic the storm shares with certain stable vortex structures in rotating fluid dynamics. It is not spinning as a rigid body. It is spinning the way a fluid mass does when it is confined at the edges and free to move at different rates at different radii. The outer clouds sweep past the inner ones, and the whole system nonetheless maintains its identity. Lightning ignites within the convective storms that sometimes form around the Great Red Spot's periphery, and within independent storm cells elsewhere in Jupiter's atmosphere. The first confirmation that Jupiter produces lightning came from the Voyager 1 flyby in 1979, when cameras recording the planet's night side caught brief optical flashes, moments of blue-white brightness erupting from within cloud features at mid-latitudes, each one an electromagnetic discharge of extraordinary energy deep in the water cloud layer. The flash itself lasts only an instant, but the radio pulse it generates travels upward through the atmosphere as a burst of emission in the kilohertz range, a wave of electromagnetic noise spreading outward from the discharge site through layers of gas and ice and cloud. Later missions detected thousands of such events across a Jovian year, concentrated most heavily at mid-latitudes rather than at the equator, and associated specifically with deep moist convective storms rather than with the broader circulation of the planet's belts and zones. The energy in a Jovian lightning discharge is not the same as a bolt of lightning on Earth. The atmospheric column on Jupiter is deeper. The charge separation that builds up within a convective cloud occurs over a larger vertical distance, and the resulting discharge is correspondingly more powerful. The radio waves it generates are detectable from orbit, spread across a range of frequencies below the threshold, where radio astronomers might otherwise try to observe the planet's magnetosphere. When a Juno instrument records a burst of kilohertz emission, the source is somewhere deep beneath the clouds, a flash that no instrument has ever directly photographed at close range, visible only as a secondary signal propagating up through the gas above it. The convective storms that host this lightning are temporary. They bloom upward from the deep atmosphere over the course of hours, disturb the cloud deck for days or weeks, and then gradually lose the updraft that sustained them as the underlying thermal anomaly that drove the convection is dispersed and the surrounding atmosphere cools back toward equilibrium. But they are not isolated events. They recur. They appear at particular latitudes where the dynamics of the underlying atmosphere create conditions favorable to deep convection again and again. The same stretch of belt may produce a convective outbreak, quiet for a year, then produce another. The storm comes and goes, but the place that makes it continues. Saturn produces its own class of convective outbreaks, distinct from Jupiter's in their periodicity and scale. The mechanisms at the root are the same: moist convection, upwelling from deep in the troposphere, but the outcomes on Saturn can be more dramatic in terms of horizontal spread. On Saturn, a major convective outbreak does not stay local. Under the right conditions, which arise roughly every 28 to 30 Saturnian years, a single convective storm source can feed a disturbance that spreads around the entire circumference of the planet. These events are called Great White Spots by tradition, named for their appearance in Earth-based telescopic records going back to the 19th century. They are bright, white, and vast. They grow from a point and become something planetary in scale. The Great White Spot outbreaks appear to be tied to Saturn's seasonal cycle. Because Saturn's orbit takes nearly 30 years, and because the planet's equatorial plane is tilted by about 27 degrees from its orbital plane, the heating pattern delivered to Saturn's atmosphere changes significantly over the course of its orbit. The summer hemisphere receives more solar energy than the winter hemisphere, and the atmospheric response to this differential heating builds over years. The best current understanding is that the periodic great white spots represent a kind of accumulated convective energy release, the atmosphere building a kind of instability through its seasonal evolution, then discharging it when a convective trigger reaches the right depth at the right time. The trigger is local, but the release is global. A convective plume rises. It pierces the ammonia cloud deck and spreads at the top. The material it spreads outward is caught by the ambient zonal winds, the broad jet streams circling the planet, and those winds carry it east. The disturbed cloud material moves faster than the source. It overtakes the source from the east, or more precisely, the source itself drifts westward relative to the eastward flowing storm material, so that eventually the front of the disturbance reaches back around the planet and catches up with the storm system that generated it. When that happens, the storm's front encounters its own wake. The cloud disturbance at that point covers the entire circumference of Saturn at that latitude. The planet is wrapped. During such an event, the appearance of Saturn changes noticeably, even in modest telescopes on Earth. A white band appears where the planet had previously shown calm cloud structure. It is not uniform, it is turbulent, braided with cloud filaments, and broken by smaller vortices that spin off from the shear between the storm material and the surrounding atmosphere. Eventually, weeks or months after the initial outbreak, the turbulence subsides. The energy disperses. The bright cloud material is mixed and diluted back into the ambient belts. The planet gradually regains something like its prior appearance, quieter, the event absorbed by the same atmosphere that produced it. Then, decades later, the cycle begins again from the same deep root. This long periodicity is part of what makes Saturn's great white spots different in character from Jupiter's more frequent convective outbreaks. On Jupiter, significant storm events occur on timescales of years or less. On Saturn, the major planet encircling events are separated by a human generation. The 1933 event was observed in modest detail with the telescopes of the time. The 1960 event built the record further. The 1990 event was observed by Voyager-era instruments, still operational, and by Earth-based telescopes that had improved substantially since the previous occurrence. And the 2010 outbreak was documented in the fullest detail yet, including by spacecraft then in orbit. Each generation of observers has encountered one of these events, and each has been able to add something to the record that the previous generation could not. There is a quality of deep time in this. The human lifetimes that have contributed to understanding Saturn's great white spots are spread across nearly 2 centuries. No single person could have watched more than 2 events. The understanding that has accumulated is not the product of any individual observation, but of many careful acts of watching placed one after another across a span of time, longer than most scientific careers. The decay of a storm on a gas giant follows its own slow logic. The outer edges of a vortex are eroded by the shear of the ambient flow, the jet streams pressing against the storm's boundary, peeling cloud filaments from its rim, mixing the storm's material with the surrounding belt. The storm loses a little of its organized structure each time this happens, but the deeper loss is in the column of sustaining convection from below. As long as the deep atmosphere continues to supply the storm with warm, buoyant, water vapor-laden gas pushing upward from below, the storm can maintain its circulation against the erosion of its outer edges. When that supply weakens, when the thermal anomaly that drove the original convection has cooled and the updraft diminishes, the storm's internal circulation begins to slow. Wind shear works on the outer boundary without renewal from below. Smaller storm filaments, spun off from convective activity nearby, can approach the aging vortex and be ingested by it. And this ingestion, while it might seem to strengthen the storm with additional angular momentum, often disrupts the carefully ordered internal structure of the vortex more than it helps. The internal circulation becomes less coherent. The storm loses its sharp boundary. It diffuses into the surrounding flow. This is how the small, short-lived storms of Jupiter's belts end. Within weeks or months, their organized rotation dispersed back into the ambient shear. It is also, presumably, how the Great Red Spot will end whenever it ends. Not in a sudden dissolution, but in a gradual weakening, a slow softening of the boundary that keeps its circulation distinct from the belts beside it, until the distinction is no longer visible, and then not there at all. The life of a storm on a gas giant can therefore be read as a slow dialogue between the energy that enters from below, convective, thermal, rising from a planetary interior that has been releasing heat since the planet formed, and the ambient shear that works at the storm's surface to disperse it. When the input from below exceeds the loss from the edges, the storm grows. When the two are balanced, the storm persists in a kind of steady state. When the ambient shear is stronger than the deep input, the storm fades. The Great Red Spot has apparently maintained something like a balance for centuries, which is why it is still there. But the balance is not static, and the slow shrinkage in its size suggests it has tilted slightly in one direction over the past 200 years. The convective plume that started all of this, that buoyant pocket of warm gas that began to rise from the water cloud layer at 5 or 10 bars of pressure, has long since been dispersed. Whatever material it carried upward has been mixed into the cloud deck, spread by the winds, cooled and settled back. The plume existed for hours. What it generated may persist for centuries. In the southern hemisphere of Jupiter, at latitude 23 degrees south, the Great Red Spot turns. One full counterclockwise rotation every 6 days. The outer cloud filaments braid and stretch at the rim. The interior churns with a differential rotation that keeps the deepest part of the vortex from moving at the same speed as the outermost ring. From far enough above, the storm looks almost still, just a red oval nested in the amber and cream of the surrounding belts, drifting slowly westward relative to the planet's rotation as the jet streams on either side guide and confine it. Its color deepens toward its center. The brick red interior grades outward through shades of ochre and pale orange before blending at the edges into the lighter material of the belt. The chemistry responsible for that color, the compound or compounds that absorb the particular wavelengths of sunlight that would otherwise reach the eye as yellow or green, leaving only red and orange, has not been definitively established. Sulfur compounds, phosphine processed by solar ultraviolet radiation at the cloud tops, complex organic molecules formed in the storm's deep interior, all remain possibilities. All have evidence for and against. The honest answer is that the reddish color of the Great Red Spot is still not fully explained, and this plain truth does nothing to diminish the storm's long, quiet, turning persistence. Below the visible cloud tops of the Great Red Spot, the storm extends downward into the troposphere, though exactly how far is not certain. Deep roots have been inferred from Juno's gravity measurements of the broader flow fields in Jupiter's southern hemisphere, but the specific vertical extent of the Great Red Spot itself remains a question that current instruments can constrain only imprecisely. It is deeper than a surface feature. It is shallower than the planet's metallic interior. where precisely it ends, at what depth its organized circulation merges with the general deep flow, is something that future measurements may eventually reveal. For now, the storm simply turns. In the cold and dark below the cloud tops, in the perpetual night of the troposphere, beneath the visible skin of the planet, the circulation continues. Layer after layer of gas moves in the counterclockwise pattern, hundreds of kilometers below the surface that any spacecraft has directly imaged, unreachable by any instrument currently in orbit, and unlit by any light that has ever crossed the space between Jupiter and the Sun. From far above, the planet is enormous and still. The great red spot is a detail. It is a small oval against a vast disk, banded in cream and amber and brown. At the scale of the full planet, even a storm wider than Earth is a modest thing, a pattern in the upper cloud layer of a world that extends downward for tens of thousands of kilometers before the gas begins to take on the properties of a metal. And yet the storm persists, turning in its slow circle, its boundary holding against the ambient shear, its interior churning in the differential rotation that keeps the outermost edge moving faster than the still and deep red center. Outside in the belt, on each side, the jet streams flow past in opposite directions. The north side of the storm is caught between one current, the south side between another. The storm is confined between them. It cannot drift far north or south. It can only orbit, carried by the zonal flow, circling the planet on its slow path. The same storm that observers in the 19th century tracked with brass telescopes through the cold night air of winter observatories. The same oval shape they sketched in notebooks that still exist in archive drawers somewhere on the surface of Earth. The storm does not know it is ancient. It does not persist out of will or endurance. It persists because the physical conditions that allow it to persist have continued. If those conditions change, if the jet streams flanking it weaken and spread, or if the deep convective input that once sustained it has finally diminished below some threshold, then the storm will fade. Slowly, without drama, its outer boundary will soften, its color will dilute, its internal circulation will become less organized, and eventually the distinction between the storm and the surrounding belt will be a matter of degree rather than kind. Then less than that, then nothing. Whether that end is near or distant, no one knows. The storm has been small enough for long enough now that researchers pay close attention to each successive measurement of its size. Some see in the data the signs of an accelerating contraction. Others see a rate of shrinkage that has not changed significantly in decades and may represent a long approach towards some smaller stable size rather than a final dissolution. The atmosphere of Jupiter does not communicate its intentions to the instruments that watch it from orbit. It simply does what it does at the pace that the physics of its enormous interior and its distant sun dictate. The long record of the storm's history is also a record of how watching improves. The measurements of its size in the mid-19th century were made by timing how long it took the storm to transit the disk of Jupiter as the planet rotated, a careful but indirect method that introduced uncertainties. Later came photography, then spacecraft imaging, then the calibrated pixel counts of instruments whose precision can be stated to the nearest kilometer. Each generation of measurement is more exact than the one before. The storm's shrinkage is a fact drawn from this long record, not from any single observation. Somewhere in the water cloud layer, 5 to 10 bars below the visible surface of Jupiter, a small thermal anomaly persists, or begins to form, or has already dispersed. It is warmer than the gas surrounding it by a fraction of a degree. In time, in hours, or days, that small difference in temperature may be enough to set a pocket of gas rising again. The column climbs through the dark. It carries moisture from the deep atmosphere and the heat of a planet that formed more than 4 billion years ago from the same slow collapse of gas and dust that built the sun. As it rises, it cools. The water vapor condenses into ice crystals. Then, above that, ammonia condenses in its turn. The cloud tops brighten where the rising gas breaks through, a white plume spreading against the pale cream of the ammonia ice layer. Below, the great red spot turns. It has been turning for as long as anyone alive has been alive, and for much longer than that. Its counterclockwise circulation wraps the interior in a slow differential rotation, the rim moving faster, the center moving slowly, the whole oval drifting westward in the confinement of its flanking jet streams. The outer filaments braid and stretch in the shear at the boundary. The color deepens toward the center. It will turn through the night, through the days that follow. The planet will complete its rotation in just under 10 hours, carrying the storm around its circuit of the southern hemisphere, while the storm itself turns counterclockwise inside that larger motion, a rotation within a rotation. The jet streams on either side will continue their flows in opposite directions. The convective updrafts from below will push or ease or quiet. The ambient shear will press on the storm's boundary as it always has, and the storm, for now, will hold its shape and carry its color and keep its ancient, patient, turning quiet. At the North Pole of Saturn, above the highest clouds, there is a shape that has no reason to exist, and yet has persisted for as long as any instrument has been trained upon it. It is a hexagon, not an approximation of one, not a rough tendency towards six-sidedness that the eye might generously read as geometric, a near-perfect six-sided polygon centered precisely on the planet's geographic pole, Kiri, each of its 6 sides running for approximately 14,500 kilometers in a nearly straight line before turning cleanly to form the next. Each single side of that figure is longer than the full diameter of Earth. The whole structure, from one corner to the opposite, spans a distance wider than our entire planet, drawn not in stone or metal, but in cloud and moving gas, and it has held that shape without measurably drifting for decades of continuous observation. The cloud bands that trace the hexagon's outline are tinted in deep golds and pale amber, set against Saturn's broader polar atmosphere, in its tones of faded cream and gray blue. From directly above, which is the view only a spacecraft can provide, the figure reads as something architectural, a chamber, a seal, a form cut from the planet's surface by some instrument of enormous precision. The interior of the hexagon contains a field of smaller cloud structures, eddies and filaments, and lighter bands crossing the polar region, and at the center of it all, locked over the pole itself, the eye of a vortex, so large and so still that it seems less like a storm than like a hole in the atmosphere, through which the planet's deep interior breathes. The hexagon was first seen by Voyager's cameras during the flybys of 1980 and 1981, when Saturn's northern hemisphere was passing through its long winter. The images were arresting, clearly structured, clearly real, and largely unexplained for many years afterward. It was not until laboratory experiments using rotating tanks of water on Earth demonstrated that polygonal jet stream configurations arise naturally from the wave dynamics of rotating fluids that a physical explanation began to take shape. In those tank experiments, a spinning cylinder of water develops regular multi-sided patterns at certain rotation rates, not 5-sided, not 7, but the precise geometry dictated by the speed and scale of the rotation. Saturn's hexagon arises from a standing atmospheric wave with exactly 6 complete oscillations locked around the pole, a configuration known as a wave number 6 Rossby wave. The wave is stationary. It does not travel around the pole the way clouds in the temperate latitudes travel with the wind. It holds its position in longitude, as if anchored, which is why the hexagon has been observed in essentially the same orientation and location from one decade to the next. 6 wave crests, 6 corners, 6 straight sides between them, each one running thousands of kilometers along the latitude before the atmosphere curves to form the next angle. The geometry is not imposed from outside. It emerges from within, from the natural dynamics of a rotating body of gas at a particular latitude, spinning at a particular speed, with nothing solid to interrupt the flow. On Earth, the polar jet stream traces a winding variable path that sometimes breaks into lobes and sometimes tightens into a near circle, its shape changing over days and weeks. On Saturn, something in the combination of the planet's rotation rate, its atmospheric depth, and the scale of the polar vortex has locked that wandering tendency into a fixed 6-sided form. The jet stream that traces the hexagon's outline flows eastward in the same direction as Saturn's rotation at roughly 100 meters per second. That is fast enough to carry any parcel of gas around the full hexagonal path in a matter of days. Yet the hexagon itself does not rotate. The gas within it moves. The wave that shapes it holds still. It is a pattern sustained by motion, the way the shape of a river's standing wave holds its form while water rushes through it continuously. The wave does not wait, the gas does not pause, and the hexagon persists. To stand at the edge of the hexagon, if such a thing could be imagined, would be to stand at a boundary as precise as any in nature. On one side, the high-latitude polar atmosphere, enclosed and organized, the cloud structures inside the hexagonal ring following their own slower circulations. On the other, the temperate atmosphere of Saturn's northern hemisphere, its broader banded structure extending away toward the equator, the familiar alternation of lighter zones and darker belts, visible from any telescope on Earth. The two regions do not freely mix. The jet stream that traces the hexagon's perimeter acts as a barrier, a wall of wind keeping the polar atmosphere largely sealed from the rest of the planet. Whatever happens inside the hexagon tends to stay inside. Whatever happens outside does not easily penetrate the boundary. For decades, perhaps for far longer, the North Pole of Saturn has been sealed in its geometric enclosure, conducting its slow interior weather in a kind of calm isolation. Inside that enclosure, at the center, where all 6 sides converge toward the pole itself, the polar vortex sits. It is not a small thing. The eye at the center of Saturn's polar vortex is roughly 2,000 kilometers across, wide enough that, laid across the surface of Earth, it would stretch from one coast of the continental United States nearly to the other. The eye is clear, or nearly so. The cloud tops drop away inside it, giving instruments trained on the pole a deeper view down into the atmosphere than is normally available. Around the eye, cloud walls rise tens of kilometers above the surrounding atmosphere, vertical towers of condensate, standing at the inner edge of the vortex's circulation, where rising gas cools and clouds form densely. From above, those walls form a bright circular rim, a collar of clouds surrounding the open eye, and the contrast between the clear interior and the dense outer walls gives the structure the appearance of a drain or a lens, a circular aperture cut through the upper cloud deck. The vortex rotates. All polar vortices do, driven by the Coriolis effect of the planet's spin. Saturn's north polar vortex rotates in the direction consistent with a cyclonic system in the northern hemisphere, counterclockwise when viewed from above. and it spins at speeds that make it one of the more vigorous circulation features in the solar system. Wind speeds in the cloud wall surrounding the eye reach values that dwarf the strongest storms on Earth, moving at many tens of meters per second in a tight, organized circulation that has shown no sign of weakening across the years of Cassini's observation. But it is the stillness of the structure, more than its speed, that settles into the mind. The polar vortex on Earth drifts, it wanders, it breaks apart in winter and reforms, it spills cold air southward when it weakens and retreats poleward when it strengthens. Saturn's polar vortex does none of these things. It is locked to the geographic pole with a precision that has no clear counterpart anywhere in the solar system, anchored there by the same deep atmospheric dynamics that hold the hexagon in place around it. The two structures nested together, the outer six-sided boundary and the inner circular eye, both stationary, both persistent, both existing in a kind of mutual reinforcement that has sustained them across timescales, longer than any living observer has had access to measure. Cassini arrived at Saturn in the northern winter, when the North Pole was turned away from the sun and lay in the cold darkness of a season that lasts nearly 15 Earth years. The hexagon, at that time, had a blue-gray tone. Not the gold and amber of Saturn's warmer latitudes, but a cooler, quieter hue, the color of a polar atmosphere receiving very little sunlight, its chemical processes running slowly, the photochemical production of haze particles reduced by the long absence of ultraviolet light. The spacecraft's instruments mapped the hexagon in infrared as well as visible wavelengths during those early years of the mission, tracing its structure through the darkness of northern winter by the heat the atmosphere itself was emitting, rather than by reflected sunlight. As the mission continued, as the years accumulated, and Saturn moved along its orbit, the northern hemisphere slowly tilted back toward the sun. The summer solstice of Saturn's northern hemisphere arrived in 2017, more than 13 years after Cassini had first entered orbit. By the final years of the mission, the hexagon's color had changed. The blue-gray of winter had given way to a golden-yellow tone, warm and deep, matching more closely the hues of Saturn's lower latitudes in their own sunlit chemistry. The Cassini team attributed the color change to the increasing ultraviolet light falling on the polar stratosphere as summer approached, driving greater production of photochemical haze particles above the hexagon, a chemical response to a seasonal change, playing out slowly across years, visible only because one spacecraft had been present and patient long enough to watch it happen. The hexagon was the same shape. The vortex was still there. The jet stream was still moving eastward at 100 meters per second. But the light had changed, and in the haze chemistry of the stratosphere above, the atmosphere had recorded that change in color, a slow chromatic shift written into the cloud deck over years of planetary time. Within the troposphere below the visible cloud layers, instruments confirmed that the hexagon extends downward, its organized circulation persisting below the ammonia cloud deck into the deeper atmospheric layers. This is not merely a surface phenomenon, not a pattern inscribed only in the visible clouds. The hexagonal wave structure reaches through the troposphere, and the warm core vortex at the center extends upward into the stratosphere as well, so that the whole system, from below the visible cloud tops to well above them, is organized around the same six-sided geometry, a column of structured atmosphere spanning hundreds of kilometers in the vertical. Most atmospheric phenomena, even large ones, are shallow relative to the depth of the atmosphere that contains them. Saturn's polar hexagon is not. It is a structure of genuine vertical extent, threading its geometry through layers that receive no sunlight and layers that receive too much, maintaining its form from the pressurized darkness below to the cold photochemical haze above. There is something in this that resists easy description. The hexagon is not the result of a collision. It did not arise because something struck the atmosphere from outside, or because some internal upheaval drove a sudden reorganization. It was not born in a moment of convective violence, or shaped by a transient disturbance. It emerged from the steady, patient mathematics of rotating fluid dynamics, the same mathematics that governs a tank of spinning water in a laboratory on Earth, the same physics that operates wherever a fluid rotates in a large enough space at a consistent enough speed. The outcome on Saturn is geometrically perfect because the underlying physics admits of a geometrically perfect solution, and Saturn's atmosphere, for reasons of scale and rotation, has settled into exactly that solution and held it. 6 is the number the physics chose. Not 5, not 7, not an approximation that wanders between the two. 6 precisely. 6 wave crests locked around the pole. 6 corners where one straight side meets the next. 6 sides each running longer than the distance from one side of Earth to the other. In the tank experiments on Earth, different rotation rates produce different polygon numbers. 3-sided, 4-sided, 5-sided patterns appear at different experimental conditions. The Rossby wave dynamics allow a range of possible outcomes depending on the fluid's speed, depth, and the rate of the underlying rotation. Saturn's particular combination of parameters, its polar jet stream speed, its atmospheric depth at those latitudes, its rotation period of approximately 10.5 hours, selects the wave number 6 solution from all the possibilities the physics allows, and the atmosphere has been presenting that solution continuously for as long as any instrument has looked. The corners of the hexagon are perhaps its most striking feature when studied closely. At each of the 6 vertices, the jet stream turns. The flow, which had been running almost perfectly straight for thousands of kilometers, curves through an angle and continues straight again in a new direction. Smaller vortices form at some of the corners, compact cyclonic cells, where the turning geometry of the jet stream creates local regions of curved flow. These corner vortices are themselves organized structures, rotating steadily within the larger geometry of the hexagonal pattern, embedded in it, the way smaller shapes can be embedded in a larger geometric form. They are not disturbances, but they are part of the pattern, products of the same wave dynamics, as much a feature of the hexagon as the straight sides themselves. Farther out from the hexagon's boundary, the polar atmosphere outside the jet stream carries its own structures. Cloud bands curve in arcs that follow the latitude lines at slightly lower latitudes than the hexagon's perimeter. Occasional smaller vortices drift in the space between the hexagon and the broader temperate band structure to the south, but these features are in a different realm. They are the ordinary turbulent life of Saturn's high-latitude atmosphere, still orderly by planetary scale standards, still organized into a recognizable pattern by the Coriolis effect and the zonal wind structure, but variable in a way the hexagon is not. They move, they change, they form and dissolve across months and years. The hexagon, at the center of them all, does none of these things. Inside the hexagon, the polar atmosphere turns with a slow interior motion, quite different from the jet stream that defines the boundary. The eye of the vortex at the very center is the calmest looking feature in the whole system, a deep open circular space where the cloud deck has parted and the atmosphere below is briefly visible. The cloud walls surrounding the eye catch what little sunlight reaches the high polar latitudes and reflect it outward so that in visible light images, the eye appears as a dark circular region rimmed by a bright collar. The contrast is sharp. The transition from the reflective wall to the open interior happens over a distance of only a few kilometers, a boundary as crisp as anything in the atmosphere of either giant planet. Below the eye, the atmosphere deepens. The infrared instruments on Cassini found a warm core descending from the polar vortex into the troposphere, a column of slightly elevated temperature aligned with the pole. A warm core vortex is self-sustaining in a way that cold core systems are not. The warmth at the center creates a local pressure gradient that drives the inward and downward circulation, which in turn generates and maintains the warmth, a loop that can persist without any external forcing, as long as the basic rotation of the planet continues to organize the flow. Saturn's polar vortex has been receiving that organizational input from the planet's rotation continuously, without interruption, for as long as any theory of its origin requires. There is no identified reason why it should stop. This is a different kind of storm than the convective outbreaks and traveling vortices found at lower latitudes. Those storms are driven by instability, by the accumulated energy of moist convection seeking a release, by temperature gradients that grow unstable and overturn. They form, they organize, they spend their energy, and over time they decay. The polar vortex is not consuming energy in the same way. It is organized by the steady rotation of the planet, maintained by the dynamics of the polar atmosphere, and the very regularity of the forcing. The planet rotates steadily, without interruption, is what allows the vortex to be so stable. A storm that is born from an instability will eventually exhaust that instability. A vortex organized by a force that never changes will tend to remain organized as long as that force persists. Saturn has been rotating for a very long time. The hexagon has, in all likelihood, been there for much of that time, or at least for an era far longer than any human instrument has existed to record it. The Voyager cameras saw it in 1980 and 1981. Cassini's instruments watched it continuously from 2004 through 2017. Between those two missions, Earth-based observations confirmed its persistence. After Cassini's mission ended, ground-based and space-based telescopes continued to observe it. In every observation, in every wavelength range, from visible to infrared, the hexagon is there. The jet stream is flowing at 100 meters per second. The vortex is sitting at the pole. The six sides are holding their shape. There is a kind of comfort in extreme persistence. A geological formation that has stood for 10,000 years feels solid in a way that a freshly built structure does not, even if the material is identical. The hexagon's persistence across decades of continuous measurement gives it the quality of something geological rather than meteorological, not a passing weather pattern, but a permanent feature of the planet, as much a part of Saturn's character as its rings, as its muted cloud banding, as the slow amber light it casts on its many moons. Cassini documented the hexagon across more than 13 years. Over that time, the spacecraft observed it in detail. No Earth-based instrument could match, mapping its cloud structure, measuring its wind speeds, probing its thermal profile, and watching the color of its clouds shift as the long Saturnian seasons turned. The scientists who worked with that data accumulated a portrait of a feature more deeply organized than its visual appearance alone suggested. The hexagon is not only a pattern in the visible cloud tops, it is a structure with vertical extent, with a thermal signature, with a self-consistent dynamics linking the jet stream at its boundary to the vortex at its center. The two features, the hexagonal jet and the polar eye, are aspects of one coherent atmospheric system, nested and mutually reinforcing, expressing in geometric form the underlying physics of a rotating planetary atmosphere at its pole. In the laboratory, when those rotating tank experiments reproduce a polygonal jet stream, the result has the quality of a small revelation, the clean, unexpected appearance of a geometric form in a medium where no geometry was imposed. The water turns, a ring of jets develops, and then the shape appears, regular and precise, in nothing but ordinary fluid, obeying ordinary physical laws. Saturn's atmosphere is doing the same thing at a scale approximately 10,000 times larger. The physics is the same, the outcome is the same. Only the size is different, and in that difference of size lies the difference between a laboratory curiosity and a structure whose individual sides are longer than the diameter of the world on which the experiment was conducted. The color shift that Cassini documented as northern summer approached, from the cool blue-gray of winter to the warm gold of summer, is a record of chemistry responding to light. Ultraviolet photons from the sun break apart molecules in the upper atmosphere and drive the formation of complex organic compounds that collect as haze. In winter, when the pole is turned away from the sun for years at a time, the ultraviolet flux is reduced, the photochemical production of haze particles slows, and the stratosphere above the hexagon clears somewhat, letting the bluer tones of the cloud deck below show through. In summer, as the sun rises higher above the northern pole, the ultraviolet flux increases, haze production accelerates, and the stratosphere above the hexagon accumulates the golden yellow compounds that color the planet's lower latitudes. The haze settles slowly. It is not a sudden change. Over years, the color gradually warms, one shade at a time, across a cloud deck thousands of kilometers across. To watch that happen, to have the good fortune of a spacecraft in orbit across more than a Saturnian decade, positioned to see the change, is to see something that no instrument before Cassini had the opportunity to witness. The Voyager flybys lasted hours. Cassini stayed for 13 years, and in that duration, the hexagon had time to show what it does across a season, to reveal that its most striking characteristic, its geometric precision, its rigid persistence, contains within it a quieter variability written in color and light, and the slow turning of a planetary year 29 times longer than our own. The North Polar Vortex, inside the hexagon's eye, spins on through all of it. Through the winter darkness, when the hexagon's clouds were blue-gray and the ultraviolet chemistry was slow. Through the long transition of the equinox, when the sun crossed Saturn's equatorial plane and the northern hemisphere began its gradual brightening. Through the approach of northern summer, when the haze deepened and the clouds began their warm chromatic shift. Through the end of Cassini's mission in September 2017, when the spacecraft made its final dive into Saturn's atmosphere and ceased to transmit. The vortex did not respond to any of these events. It continued to spin, organized by the geometry of the planet's rotation, sustained by the warm core descending through the troposphere, enclosed by the hexagonal jet stream, flowing steadily at 100 meters per second around its perimeter. It is still there now. The instruments that have turned toward Saturn's north pole since Cassini's end have confirmed the hexagon's persistence. The shape is still six-sided. The jet stream is still eastward. The vortex is still centered on the pole. Whatever color the clouds have taken on as the northern summer deepens is not yet fully measured, but the structure that holds those clouds in their geometric arrangement has not changed in any way any instrument has been able to detect. It is simply there, as it was when Voyager first photographed it, as it presumably was long before any camera had looked. There is a word for things that persist at the scale of planets without visible cause for their persistence, things that outlast the instruments that measure them, the people who interpret the measurements, and the institutions that fund the instruments. The word is simply old. The hexagon is old in the way that geological features are old, in the way that deep ocean water circulates without hurry through an unchanging darkness. It has been there long enough that its origin is not well constrained by observation, only by inference from the physics of rotating fluids and the known dynamics of giant planet atmospheres. Theory says it could persist for a very long time under the right conditions. The conditions at Saturn's North Pole appear to be, and to have been, exactly right. 6 sides, 100 meters per second, an eye 2,000 kilometers across, cloud walls rising tens of kilometers above the surrounding atmosphere, a warm core threading downward into the troposphere, a stratosphere above that fills slowly with golden haze as the decades-long summer arrives. The whole system sitting at the pole of a planet nearly 10 times Earth's diameter, held together by forces that have been operating without interruption since before the planet's present cloud deck formed. The hexagon does not require attention to persist. It does not require observation or measurement or understanding. It simply continues, the jet stream flowing along each of its 6 sides in turn, the corners holding their angles, the vortex spinning at the center. On the night side of Saturn, where no sunlight falls, and the clouds emit only the faint infrared glow of their own warmth, the hexagon is still there, invisible to the eye, but present in the thermal structure of the atmosphere, in the wave that holds its geometry in place, and in the stratosphere above it, settled into the cold and thin air above the cloud tops. The haze particles formed by sunlight from a star 150 million kilometers away drift slowly downward toward the clouds below. They are gold-yellow in color, a tint of warmth in an atmosphere otherwise pale and cold. They fall with great slowness in the low gravity of Saturn's upper air, taking months or years to descend a single kilometer. They settle into the cloud tops. They color the hexagon's upper surface in that warm, muted amber that Cassini watched develop as the northern summer approached. The color deepens, the season continues. The jet stream flows along its 6 sides at 100 meters per second, turning cleanly at each of 6 corners, returning to where it began, and beginning again. The wave that holds the shape does not drift. The vortex at the center does not wander. The cloud walls around the eye stand at their full height, bright at their tops where the light reaches them, darkening rapidly as the eye's interior deepens. In the polar night, in the polar summer, in the long transitional seasons between, the hexagon holds its geometry against the slow turning of the planet, patient and orderly and ancient, as precise as mathematics, as enduring as the rotation it is built from, as quiet as the cold space that surrounds it on every side. In March of 1979, a spacecraft moving at tens of kilometers per second carried a camera toward Jupiter, and the planet grew. It grew from a point of light into a disk, and from a disk into a world, and from a world into something that had never existed for human eyes before, a place close enough to read, its cloud bands resolving into texture and color, and the fine braided detail of weather on a scale no one had seen. The cameras kept returning images across the hours of closest approach, and in those images, the pale cream zones and the burnt amber belts sharpened into a reality that maps and telescopic drawings had only approximated. Jupiter was no longer a bright object in the night sky. It was a world with a surface that moved. Voyager 1 swept past in March of that year, and Voyager 2 followed in July. Between them, they carried back more information about Jupiter's atmosphere than all the centuries of ground-based observation that had preceded them. The equatorial jet stream, long inferred from the drift of cloud features visible through telescopes, was measured directly for the first time, a river of gas moving at roughly 150 meters per second at the cloud tops, confirmed by tracking discrete features from one image to the next as the cloud slid eastward against the slower rotation of the planet's deeper layers. The great red spot was seen in close detail, its outer edges braided with spiraling cloud filaments, its interior a deep reddish oval that rotated slowly counterclockwise over a period close to 6 days. And on the planet's night side, where the cameras caught the darkness between Terminator and Shadow, something else appeared. Brief flashes of blue-white light, concentrated and then gone. Lightning on Jupiter confirmed for the first time the same electrical discharge that crosses the sky in a summer thunderstorm on Earth, but generated deep in the water cloud layer of a planet more than 11 times Earth's width, and carrying energies that dwarfed anything the inner solar system's smaller worlds could produce. The two spacecraft moved on to Saturn, arriving in November 1980 and August 1981. There, the cloud feature tracking continued, and what it revealed about Saturn's equatorial wind system exceeded anything measured at Jupiter. The equatorial jet on Saturn moved at close to 400 to 500 meters per second, nearly half a kilometer every second, sustained and continuous, encircling a planet 9 times the diameter of Earth in an unbroken loop. The banding was softer than Jupiter's, its edges blurred by high-altitude haze into gradients of tan and pale gold, rather than the sharp color transitions visible at Jupiter. But the organization was unmistakable, alternating prograde and retrograde jets, a planetary-scale structure of rivers and counter-rivers laid in parallel bands across the visible cloud tops. Saturn's polar regions were not fully accessible to the Voyager cameras, given the geometry of the flybys, and so the hexagon at the North Pole waited. It was present in the Voyager data, detected in thermal infrared images that mapped the North Pole from the angles available, but its full geometric form and its scale would not be widely appreciated until the decades that followed. What Voyager gave was the broad outline: 2 giant planets with organized deep wind systems, extraordinary storm structures, and weather on a scale that had no counterpart in the inner solar system. The image count measured in thousands. The transformation in understanding measured in something that has no unit. Years passed between the Voyager flybys and the next deep examination of Jupiter. 16 years in which ground-based observers continued their patient watch, recording the drift and evolution of cloud features, noting the emergence and decay of storm systems, measuring the slow changes in the width and color of the belts. The Association of Lunar and Planetary Observers and the British Astronomical Association accumulated records across those years, drawings, photographs, and eventually digital images, building a continuous archive that no single spacecraft mission could have supplied. A spacecraft visits for months or years. Ground observers visit every night. The sky is clear, across decades, accumulating the long baseline that reveals changes too slow to catch in any single observing campaign. In December of 1995, a small metallic cylinder entered Jupiter's atmosphere from above, trailing a parachute that opened against the increasingly dense gas above the ammonia cloud deck. The Galileo atmospheric probe had traveled for 6 years to reach this moment. Its instruments began sampling the atmosphere through which it descended, measuring temperature, pressure, wind speed, the abundances of individual gases, the character of the cloud layers through which it passed. For approximately 58 minutes, data flowed upward from the probe to the Galileo orbiter waiting above, and from there to Earth. Then the pressure became too great, and the probe was compressed into silence at roughly 22 bars, 22 times the atmospheric pressure at Earth's sea level, still far above the predicted base of the water cloud layer it had been designed partly to characterize. What the probe found rewrote several things that had been assumed about Jupiter's atmosphere and confirmed one thing that had been suspected. The winds grew stronger with depth rather than weaker. At the cloud tops, wind speeds were already substantial. Below them, the probe measured wind speeds exceeding 170 meters per second, faster than the surface winds at the cloud level, moving in the same eastward direction as the equatorial jet above. This was unexpected. It suggested the winds were not driven primarily by solar heating at the cloud tops, which would have predicted weakening with depth, but were instead expressions of a deeper organized structure extending well below the visible atmosphere. The probe had entered a region of locally dry, descending atmosphere, an area known as a hotspot, and the measurements it returned were not representative of Jupiter's global average. But the depth of the winds was real, and it pointed toward a truth that later missions would confirm. By the time the Galileo probe transmitted its last measurement, the spacecraft carrying its relay antenna had settled into an orbit that would keep it circling Jupiter for nearly 8 years, mapping the planet's cloud structures, measuring its magnetic field, and watching its weather evolve across time. The Great Red Spot persisted. Belt structures widened and narrowed. Storm systems appeared, drifted in the zonal wind, and dissipated. The long patience of continuous observation from orbit revealed what any single flyby photograph could not: that Jupiter's atmosphere was not a static image, but a slow-moving record of dynamics operating on timescales from hours to centuries. On Saturn, a different spacecraft was making its way across the outer solar system. Cassini arrived at Saturn in July of 2004 after a journey of nearly 7 years, and what followed was 13 years of continuous orbital observation, the longest single sustained study of a gas giant atmosphere ever conducted. The spacecraft carried instruments sensitive to wavelengths from ultraviolet, through visible light, through infrared, through microwave, and each instrument peeled away a different layer of what Saturn's atmosphere actually was. The North Polar hexagon came into full view in Cassini's data from the beginning. Each of its 6 sides ran for approximately 14,500 kilometers, longer than the diameter of Earth, and the structure as a whole sat centered precisely on Saturn's geographic North Pole, rotating with the planet, but holding its 6-sided geometry unchanged. Cassini could watch it across time in a way no earlier mission had been able to do. The hexagon's color was documented in the early years of the mission as a cool blue-gray, consistent with the low solar illumination of Saturn's northern winter. As Saturn moved through its orbit and northern summer approached, the color of the hexagon shifted, a slow progression across years, from the cooler tones toward a warm golden yellow, driven by the increasing ultraviolet radiation of the oncoming summer, stimulating greater production of photochemical haze in the stratosphere above. The Cassini infrared mapping instrument confirmed that the hexagon extended downward below the visible cloud tops through the troposphere, and that a warm core vortex sat above it in the stratosphere, a vertically extensive system spanning from below the clouds to well above them. At the center of the hexagon, the polar vortex waited, a circular eye approximately 2,000 kilometers across, surrounded by cloud walls rising tens of kilometers above the surrounding atmosphere. The eye itself was relatively clear, its interior looking downward into a deeper layer than the cloud walls permitted from the sides. The geometry was precise and still, a circular opening at the top of Saturn's atmosphere above the pole, bounded by rising cloud structures as sharply defined as anything in the planet's visible disk. Cassini imaged it across the mission in multiple wavelengths, watching it hold its shape through Saturn's seasons, unchanging in its broad form, even as the color of the surrounding hexagonal structure slowly warmed. Then, in December of 2010, Saturn's northern hemisphere broke open. A convective plume erupted from a single source in the northern temperate latitudes, a column of gas rising from the deep atmosphere, punching upward through the cloud layers and blossoming at the visible cloud tops as a brilliant white outburst that grew within days into a storm head thousands of kilometers across. The instruments aboard Cassini were already watching when it began, positioned by luck and orbital geometry to catch the earliest stages of an event that would become one of the most extensively documented weather phenomena ever recorded on another planet. The storm was a great white spot, a class of periodic convective outbreaks on Saturn that recur approximately every 28 to 30 Saturnian years, each one triggered by the accumulated buildup of latent heat in the deep atmosphere over the decades since the previous outbreak. The 2010 event was the first such storm to occur during an active orbital mission. Within weeks, the turbulent wake of the storm had spread eastward in Saturn's equatorial winds, carried around the planet by the zonal flow until the disturbed cloud material had encircled the entire globe. Saturn, a planet so wide that Earth would fit inside it 9 times, was girdled by a single storm system's debris within a matter of weeks. Cassini's cameras recorded the full evolution, the initial bright plume, the spreading turbulent wake, the wrapping of the disturbance around the planet, and eventually the complex evolution of the storm's head as it propagated eastward and began interacting with its own eastward spreading tail. Radio detectors aboard the spacecraft picked up the electromagnetic signatures of lightning within the storm, bursts of emission confirming that the deep convection driving the outburst was producing electrical discharges on the scale that only Jupiter had previously been known to generate. Cassini remained at Saturn until September of 2017, when, fuel depleted and the mission complete, the spacecraft was directed into Saturn's atmosphere in a final descent that ended with its destruction at depth, a deliberate choice made to avoid contaminating Saturn's moons with any residual terrestrial material. In the final days of the mission, Cassini flew a series of orbits that passed between Saturn and its innermost rings, closer to the planet's cloud tops than any spacecraft had gone before. The data from those final passes returned measurements of Saturn's gravitational field at a resolution that allowed scientists to probe the depth of its zonal jet streams, extending the understanding of how deep Saturn's organized winds actually reach into the planet's interior. Across the years of Cassini's mission at Saturn, Juno was being built and launched toward Jupiter. The spacecraft entered orbit around Jupiter in July of 2016 in an orbit designed to carry it repeatedly from pole to pole, passing close over the cloud tops at the equator and arcing out into space above the poles, where the radiation environment was least damaging to its instruments. Each close pass returned data from an altitude of a few thousand kilometers above the cloud tops, giving the microwave radiometer instrument aboard a clear view of the thermal emission rising from deep within the atmosphere at multiple depths simultaneously. What the microwave radiometer found confirmed what the Galileo probe's wind measurements had hinted at. Jupiter's zonal jet streams, The alternating east-west flows that produce the visible banding extend to depths of at least 3,000 kilometers below the visible cloud level. Not shallow weather layer features confined to the cloud-forming region in the top few hundred kilometers, but deep atmospheric structures penetrating the planet's interior to depths where pressures climb to hundreds of thousands of times Earth's surface pressure. The organized pattern of the belts and zones visible at the cloud tops is the surface expression of something reaching far deeper than sunlight or the eye can follow. The same gravity field measurements that revealed the depth of Jupiter's jet streams also pointed toward where those jets finally end. At depths where pressures approach approximately 100,000 bars, 100,000 times the pressure of Earth's sea level, the hydrogen that makes up most of Jupiter's atmosphere transitions to a metallic conducting state, and the planet's interior begins to rotate as something closer to a solid body. The organized differential rotation of the jet streams above becomes impossible to sustain against the electromagnetic coupling between the conducting fluid and the planet's magnetic field, and the jets fade into the rigid rotation of the metallic interior. The visible cloud bands, stretching overhead in pale cream and amber, are anchored 30,000 kilometers below in the transition to liquid metal. Juno's microwave radiometer also found something unexpected about the distribution of ammonia within Jupiter's atmosphere, below the visible ammonia ice cloud layer, in the region where cloud tracking methods and the Galileo probe had suggested a relatively uniform mixing of ammonia gas through the troposphere. The radiometer found a concentration that was anything but uniform. Ammonia was gathered into a broad column centered on Jupiter's equator, a deep plume of elevated ammonia abundance extending downward to at least 300 kilometers below the cloud tops, while at mid-latitudes, the ammonia was depleted at depth below the cloud layer. This structure, which scientists called the equatorial deep plume, had no direct counterpart in the atmospheres of Earth or any other well-studied world. It appeared to be the product of a deep convective organization shaped by Jupiter's rotation, the planet's spin, sorting the vertical transport of gas into a pattern that reflected not just the local thermodynamics, but the global structure of the planet's interior circulation. The Juno cameras, designed primarily for public outreach, but capable of resolving fine cloud detail from close range, returned images of Jupiter's cloud tops that showed texture no previous mission had captured. Along the edges of the north equatorial belt, where the belt meets the pale zone to its north, Cassini's imaging had shown braided filamentary structures, interlocking streams of cloud folded into complex overlapping patterns. From Juno's closer vantage, those structures resolved into something still more intricate: fine-scale vortex filaments, eddies and counter-eddies, streamers of cream and ochre drawn into loops and spirals by the shear between adjacent wind streams. The atmosphere of Jupiter, seen from close, was a surface of extraordinary complexity, not chaotic, but organized at every scale into structures that repeated and nested within each other, from the planet-spanning belts down to the smallest features the cameras could resolve. Between spacecraft visits, the ground-based observers continued their watch. Amateur astronomers in North America, Europe, Japan, and Australia, operating from backyard observatories and community telescope sites, adapted their instruments over the decades to keep pace with the improving technology available to them. By the early years of the 21st century, high frame rate cameras attached to telescope eyepieces allowed the capture of thousands of short exposure images in a single observing session, which could then be combined computationally to cancel the blurring effect of Earth's atmosphere and produce images of Jupiter and Saturn sharp enough to show belt disturbances, storm outbreaks, and the oval features drifting in the south temperate belt. The South Equatorial Belt Revival of 2010, in which Jupiter's most prominent southern belt, which had faded to near invisibility the previous year, rapidly reappeared in a complex and still not fully understood sequence of convective activity, was documented in real time by ground observers across multiple continents before Juno was even launched. One observer at a telescope in the pre-dawn hours can see things that no spacecraft currently in orbit is positioned to record. The combination of ground-based monitoring carried forward continuously across decades, with the deep, close, physically penetrating measurements returned by orbital missions, creates a picture that neither source could build alone. The historical archive of ground observation documents the long baseline evolution of Jupiter's atmosphere across centuries, the slow shrinkage of the Great Red Spot, the periodic revival and fading of equatorial belts, the recurrence intervals of Saturnian Great White Spot outbreaks. The orbital mission provides the depth, the atmospheric chemistry, the gravity field, the microwave sounding below the clouds. Each informs the other. The Great Red Spot's history is legible in that long archive. Observations from the 1830s onward show an oval of considerable east-west extent, estimates placing it at roughly 40,000 kilometers across in the 19th century, large enough at that scale to contain 3 Earths, side by side, with room remaining between them. Over the following century and a half, it shrank. The shrinkage was not linear, but the trend was consistent, and by the early 21st century, the storm's east-west extent had fallen to roughly 14,000 to 16,000 kilometers. It remained an anticyclonic vortex, rotating counterclockwise over approximately 6 days, its outer edges still braided with cloud filaments drawn in and deflected by the storm's circulation, its interior still carrying the reddish-orange coloration that has made it the most recognizable feature of Jupiter's visible disk. Whether the shrinkage will continue and whether the Great Red Spot will eventually disappear entirely is a question the archive cannot answer. The dynamics driving the contraction are not fully understood. The storm has been losing the small vortices from the surrounding belt region that may once have provided sustaining input to its circulation, but it has also persisted through conditions that might have been expected to end it many times before, and the record of its previous longevity offers no clear guide to its future. Saturn's periodic storms, documented across the historical archive in their roughly 28 to 30-year recurrence pattern, have their own long baseline story. The 2010 Great White Spot was the 7th major outbreak in the historical record, the previous ones occurring in 1876, 1903, 1933, 1960, and 1990, with some variation in exact dates and a degree of uncertainty in the older records. The recurrence interval corresponds closely to Saturn's orbital period of 29, 5 years, 1 outbreak per Saturnian year, timed to the season, concentrated in northern summer when the convective instability in the deep atmosphere reaches its peak. The regularity of the pattern suggests that the outbreaks are governed by the slow accumulation of heat in the deep troposphere across Saturn's long year, eventually reaching a threshold at which the stored energy can no longer be contained by the stable layers above, and breaks through in a single violent convective eruption. Whether the 2010 event exhausted the buildup completely, or whether the cycle has reset for a future outbreak in the vicinity of the late 21st century, is among the questions the long archive will need another generation of observers to answer. What has been built across the decades from Voyager to Juno and Cassini is a picture of two planets whose atmospheres are organized by forces operating simultaneously at every scale, from the planetary interior, where metallic hydrogen, rotating as a near-solid body, sets the boundary condition for all the fluid dynamics above, up through the deep troposphere, where zonal jets 3,000 kilometers tall carry organized flow through perpetual darkness, through the cloud-forming layers where ammonia ice and ammonium hydrosulfide and water condense in sequence from warm depths to cold heights, and finally to the visible cloud tops where the whole deep architecture is written in the colors and motions of cloud bands that sunlight can reach and cameras can photograph. Every visible feature is the surface expression of something deeper. Every measurement at the cloud top is a clue to what lies below. The Galileo probe fell through 22 bars of pressure and transmitted for 58 minutes before the atmosphere closed over it. It measured what it passed through, and what it measured reshaped the picture of the planet it entered. The information did not diminish when the probe went silent. It moved into the archive, into the equations describing zonal jet dynamics, into the calibration of the microwave radiometer that Juno would carry 20 years later. Knowledge built across instruments and decades does not dissipate when the instrument goes quiet. It settles into the next question. Juno continues to orbit Jupiter, its orbit adjusted periodically to extend the mission beyond its original design life. Each close polar pass returning new microwave soundings and new camera images. The microwave radiometer continues to map the deep ammonia distribution, filling in the latitudinal and longitudinal coverage that accumulates orbit by orbit. The fine-scale cloud images continue to document the evolving texture of the equatorial region and the polar cyclone clusters, the tight-packed oval storms, locked in geometric arrangements at both poles, discovered during the mission's early passes and monitored in their stability and slow evolution since. Saturn, without an orbiting spacecraft since Cassini's descent in 2017, continues to be watched from the ground and from time to time by space telescopes capable of resolving its disk in wavelengths spanning from ultraviolet through infrared. Its hexagon persists at the North Pole, holding its six-sided form through the years since Cassini's departure, the long-established pattern of its standing Rossby wave, unchanged by the absence of an observer. Saturn's south polar region, less well characterized than its northern counterpart, has shown evidence of a similar, but less perfectly geometric polar vortex structure, a feature observed in Cassini data and monitored from the ground where resolution permits. Somewhere in the deep interior of both planets, below the reach of any instrument currently in operation or planned, the pressures and temperatures approach the conditions where hydrogen and helium begin to behave in ways that have no straightforward laboratory counterpart. The metallic hydrogen layer in Jupiter's interior, conducting electricity as a liquid metal, generates the planet's powerful magnetic field through a dynamo process broadly analogous to the one that generates Earth's magnetic field in its liquid iron outer core, but occurring at a scale and under conditions vastly different from anything accessible to direct measurement. The coupling between that conducting interior and the overlying atmospheric jet streams, the electromagnetic braking that sets the depth at which organized differential rotation gives way to solid body rotation, is understood in its broad outlines from the Juno gravity measurements. But the detailed physics of the transition remains an active area of theoretical work. There is something at rest in the patience that this science requires. The orbital period of Jupiter is close to 12 years. The orbital period of Saturn is 29, 5 years, a phenomenon that occurs once per planetary orbit, a great white spot, a seasonal color change in Saturn's polar hexagon, a revival of Jupiter's south equatorial belt, tied to the approach of a particular Jovian season, cannot be studied in a human career without the accumulated archive of observers who came before. The record of Saturn's great white spot outbreaks was built by people who did not know each other, working a century apart, keeping notes in different languages about the same white plume erupting from the same general latitude in northern Saturn for the same deep thermodynamic reason. Their observations, aggregated, become a dataset. The dataset becomes a recurrence interval. The recurrence interval becomes a physical constraint on models of Saturn's deep troposphere. The watches continue. On a clear night, from a dark site, where the atmosphere above is steady and the seeing is good, a telescope of moderate aperture resolves Jupiter into a disk showing belt detail. The north and south equatorial belts, the great red spot, if it is on the visible hemisphere, the oval features in the south temperate belt drifting in the zonal flow, and the fine braided texture of the folded filamentary regions along the belt edges. The image shifts and shimmers slightly with the motion of Earth's atmosphere, but the high frame rate camera catches the moments of best definition, and the software draws a sharp image from the accumulated frames. The same planet that Galileo turned a crude telescope toward in 1610, resolving it into a disk with moons, is the planet in that image. The same oval storm that 19th century observers sketched with careful pens, noting its longitude and its reddish hue, is still there, diminished in size, continuing to shrink, but present and rotating at the same latitude, in the same belt, still an anticyclone, still red. The archive is continuous. The watching is the same watching, conducted across 4 centuries, with instruments of increasing precision by people who shared nothing but the same interest in what was there. Saturn rises later. Its disk, smaller and more distant, shows less detail at most amateur apertures, but the ring system catches light beautifully, and the planet's banded disk is visible under good conditions, the pale equatorial zone and the darker adjacent belts soft and gradated compared to Jupiter's sharper contrasts. On a night of exceptional seeing, belt detail sharpens, and faint storm features become detectable as slight brightness irregularities in the cloud banding. The North Polar region, where the hexagon persists, is not directly resolvable from Earth's surface in a backyard instrument. It exists at a scale and latitude that requires either an orbiting spacecraft or the largest ground-based telescopes with adaptive optics to resolve clearly. But it is there. It has been there since Voyager detected it. It was there before Voyager. It holds its six-sided form in the polar atmosphere, whether or not an instrument is watching it, following the physics of a rotating fluid in a way that needs no observer to remain true. The 2 planets wheel on in their slow orbits, Jupiter completing 1 circuit of the Sun in roughly 12 years, Saturn in 29. 5. Carrying their atmospheres and their organized wind systems and their ancient storms and their polar geometric forms through the outer solar system in paths that have been stable for billions of years. The great red spot rotates. The north polar hexagon of Saturn holds its 6-sided shape. The zonal jets on both planets carry their organized flow from the visible cloud tops downward through thousands of kilometers of darkness to the boundary with the metallic interior. Lightning discharges in Jupiter's mid-latitude water clouds and sends radio pulses propagating upward through the ammonia haze toward space. A convective plume stirs somewhere in the deep troposphere of Saturn, warming and rising, still too small to be visible, but laying the slow groundwork of a process that will take decades to reach the surface. From any given point on Earth on a clear night, one or both planets are visible for part of the year, Jupiter a steady cream-white point among the stars, Saturn a softer gold one, both moving slowly against the fixed background of the constellations along the path the solar system's plane describes across the sky. They have been watched from this surface since before there were instruments to sharpen the watching, noted as bright wandering stars among the fixed ones, tracked across the sky by observers who recorded their positions without knowing what the positions meant. The knowing came later. It accumulated slowly, built from each observation added to the one before it, from Galileo's first resolution of Jupiter into a disk with moons, through Cassini's discovery of Saturn's gap, through the Voyager images, the Galileo probe, the Cassini mission, Juno. Each layer of knowledge settled over the previous one like sediment, patient and cumulative, until what had once been two bright wandering lights resolved into two worlds of extraordinary depth and complexity. The watching goes on now, as it always has, in backyard observatories and professional facilities, through ground telescopes and the archived data of past spacecraft and the ongoing measurements of current ones. Jupiter turns on its axis in less than 10 hours, bringing new cloud regions into view every few hours as the planet rotates. Saturn turns in a little more than 10. The storms that were visible last night have moved. The great red spot has drifted a little further in its slow orbit around the planet's south equatorial belt. The north polar hexagon of Saturn sits still and six-sided above the pole, exactly where it was when the observations that first documented it were made, and exactly where it will be for as long as the physics that holds it there continues to hold. The light reaching an observer's eye from Jupiter left the planet more than half an hour ago, depending on where in their respective orbits Earth and Jupiter happen to be.